Great, it's fun. Great. Is there anybody on? Going otherwise? Can you go? I'll let them check. Great. Start. Yeah. Okay. Well, welcome everyone. I'm Steve Plimpton. Used to be at Sandia. Have an adjunct appointment here at Temple, one of the LAMMPS developers. So happy to be part of the workshop that Axel has organized and to meet many of you that are here in person. We had a nice dinner last night. I view my talk as kind of a complement to what Stan talked about yesterday. He was talking about optimizing kernels in an HP simulation code, in particular LAMMPS, on GPUs or with OpenMP threading. And so that's kind of focusing on the core kernels of your code and getting them to run well on that specific hardware. So now I'm going to kind of go up a level and talk about the MPI level, where you need to do communication between MPI tasks in support of making those compute kernels as fast as possible. So let's go to the next slide here. I'm going to break this into two talks like Stan did yesterday. We'll take a break in between. I think the first talk is actually a little shorter than the second talk, so maybe our break will be a little sooner rather than later. But in the first talk, I'm going to talk about four what I call patterns for different kinds of MPI level communication in a code, particularly scientific codes. So that's regular, irregular, rendezvous, and ring. And I'll explain each of those in some detail in this talk. And in the second half, I'll make it more specific to LAMMPS, show how those patterns are used in LAMMPS itself. And they're not just limited to LAMMPS, they're useful in other codes. So I have an illustration or two of other kinds of scientific simulations or analyses where these patterns might be useful. And then finally, I'll give you some code level implementation details if you want to dive into the LAMMPS source code a little, or maybe you want to do some development yourself in LAMMPS and being able to see how some of those methods work, I think could be useful. So I'll primarily talk about LAMMPS when I'm talking about specific codes, but I'm also going to talk about another particle-based code called Sparta. And when we get to that point in the second talk, I'll tell you just a little bit about the methods that code uses. So I want to emphasize that these are communication patterns, not just for molecular dynamics codes, really not just for particle-based codes, but I think they're relevant to many HPC codes that do physical simulation of different kinds. So I think the basic ideas of these patterns might appear in many of those codes. So whether you're a user or whether you're a developer, and maybe you'll at some point sooner or later work on other codes as well, and I think it's helpful to have an understanding of some of these patterns. So first, let's motivate this whole topic a little bit. Why does parallel communication matter in the MPI level? Well, most parallel HPC codes, simulation codes, are compute dominated. Sometimes that can involve memory bandwidth issues, so you're spending all your time grabbing data out of memory and doing computations on it. At least that's what you'd like to be spending most of the time on to make it efficient. So the performance of the kernels on a single compute node is critical to that, and that was Stan's focus yesterday in his nice talks. So that can either be on a single CPU where you have some number of MPI tasks, maybe you're doing additional threading on each MPI task to get more parallelism out of that individual task, or it can be on a single GPU where you're launching these kernels. Cocos is useful in both of those contexts because the same code is portable across different backends, whether that's threads, OpenMP threads, or whether that's GPU languages for different hardware vendors. The same code, if you cocosized it, can be optimized for all those different kinds of hardware. So the goal then, when you think about your simulation at the largest scale, is you want to partition the work across these compute units in a way that you need minimal parallel communication to support it. And if you can do that, then the computations themselves are going to be pretty well load balanced. You've got maybe 10 GPUs or 1,000 GPUs or 1,000 threaded CPUs working on your simulation, and they all have, when you get to that point in the computation, an equal amount of work to do. And hopefully the computations are in big chunks, like Stan talked about yesterday. To fully fill up a GPU and use it optimally, you need a fairly hefty size of work to pass to it. And so you want those big chunks to be ideally uninterrupted by any communication, or at least there's other ways to actually overlap the communication sometimes with the computation. But for simplicity, just think of doing some communication, then you have a big chunk of work. Processor, the GPU can work on that for a while and then come back and do more communication in that way. So if you can do that, then the computational speed is maximized, especially if you use topos like Stan talked about, and hopefully your communication cost is minimized. That's the goal of these patterns of communication that I'm going to talk about. So, as we'll see in a couple of the examples, sometimes this requires different decompositions of the work and the data for different computational tasks. So in that context, the parallel communication can be used to switch the decomposition from one to another, so you're set up for the next computational task, and then it's a big chunk of work that will hopefully run well on the GPU receiver. Okay, so all that makes sense in terms of kind of motivating the reason to think about the parallel communication in your code? Okay, so the next thing that's kind of a precursor to thinking about the communication that's needed is to figure out how your simulation is decomposed and the work that it does across processors. So I'm going to show you 3 or 4 different options for the way LAMMPS does that. And basically, they're all spatial decomposition methods. So you're taking a simulation box, it has some atoms in it, and you want to partition that box and the atoms in it, and so each processor owns some of them and do computational work on. So I think Stan might have showed this little diagram yesterday. Here's 3 little examples. So this is a flat substrate, and if these little pictures are periodic, a flat substrate, and it has some post that's sticking up, and as that's replicated in parallel, it's like a little array of posts projecting out of a flat substrate. So as you can see, if you put a simulation box around the smallest periodic unit of that, you have a lot of processors on the left, a lot of processors with empty domains. There's no atoms in the domain. So what I'm showing here with the yellow lines is a partitioning of the simulation box and the atoms, so that in this case, there's 16 cores that are sharing that simulation. You just do the simple thing, which is the default in LAMMPS, a regular grid of processors, say 4x4 and 2D, then you get a good amount of work in most of the processors, but in several of them. So to make that more work balanced, LAMMPS has a couple of options. And one is that you keep the regular 4x4 grid topology, but you shift the lines, the vertical lines and horizontal lines, so that you vary the size of those partitions. And so now you can see there's only 2 as opposed to 4 or 5 or 6 domains that are empty, and your more balanced processors. Most of the processors have about the same work to do, which is still some that are idle. And so the next idea is called recursive coordinate bisectioning, and I'll explain the algorithm a little bit in a moment. But now the goal is to partition in a recursive way and kind of tile the simulation with little domain in 2D with little regular rectangles, but do it in a way that each rectangle has exactly the same number of atoms. So it may not look like that, but if you look at the one in the upper right, it has a row of purple atoms that's pretty wide at the bottom, and that's just as many atoms as are in these tiny boxes in the lower left. So let's see if this is the way. Yeah, this is where I'm going to tell you a little bit how this works. So let's see if I can do it with that pointer. Can you see my pointer there? So the way recursive coordinate bisectioning works, let's start with the coordinate part. So coordinate means that you pick one of the axes, X, Y, or Z. Typically, it's the longest one. This is a square, so you could pick either one. But we're going to partition the simulation domain along that axis, and we're going to bisection it. You choose a cut. It puts half the atoms on one side and half on the other. So in this case, that partitioning was here at the bottom. So this line was chosen in the Y direction, and then the position of this line vertically was chosen to put half the atoms above and half the atoms below. So that position was right here. And then the recursive part is we now put 8 of the processors below the line, we put 8 of the processors above, We now have a rectangle again that's above, two rectangles above and below, but we're going to recurse down this tree. And so we're going to let each of these 8 processors above choose where to partition, this time in the X direction. And so that's going to be done with this vertical line here, and that puts 4 processors to the left, 4 processors to the right. Down here, this is why it becomes a kind of irregular tiling. These 8 processors here decided to draw that partitioning line, that bisector right here, the 4 processors on the left, 4 processors up. So now you recurse, you have little sets of 2 processors, or you want to take groups of 4 processors, split them into 2 each, and finally the 2 processor boxes, split them into 1 each. And again, each time you choose a coordinate direction, you choose where the bisector is, and you try to assign half the atoms. So if you're doing this on 17 processors, you can just put 9 and 8 processors and make a bisection that's appropriate. You can vary this for any number of processors in any shape domain. So that's how this partitioning ends up with, the subdomains are different sizes, but it's just a tiling of 2D rectangles. In 3D, it would be a tiling of 3D bricks to build a simulation domain. So now the same idea works when we're actually doing triclinic shaped domains, not orthogonal boxes. So on the left is the same, this is the first time I've shown it. On the left is a triclinic box, so it looks like an orthogonal box that's been skewed to one side. So we're doing that on 16 processors, doing it with the regular grid approach. It would look like exactly the same. The lines just tilt with the box. And so each processor subdomain is this little skewed rectangle, I guess, a parallelogram in 2D that is consistent with the shape of the overall box. So if it was 3D, these would be little parallelepipeds, which are, can be sheared in this direction and this direction and third direction. So there's actually 3 kinds of tilts you can apply to the box. But the point is, in an orthogonal box, the edge vectors of the box A, B, and C are orthogonal to each other, and they're actually aligned with the coordinate axes. Here, the box edge vectors, which would be along the bottom here and along here, are now no longer normal to each other. There can be these tilts applied so that they're in different directions. That still defines a parallelepiped in 3D. So we wouldn't run this kind of coarse-grained water simulation, which I'm going to show you some pictures of and movies of a little later. We wouldn't run that typically in a triclinic box, but if we did have a system like that that was skewed with this recursive coordinate bisectioning decomposition, it would be exactly the same thing. All the lines would tilt over, and the RCB algorithm would still work in that tilted space to partition and put the planes in each dimension. So you would just make it look like the diagram on the left, where all the vertical lines would be skewed to the right to be parallel to the box edges.
Steve, when you actually do that, do you do it in lambda space or in?
Yep. So what you do is you actually convert the triclinic space into lambda space. So conceptually, the box is now 0 to 1 in each dimension, and you can do exactly the same RCD with that partition where you want it, say, at 0.7, and then if the box gets tilted back, it's effectively a domain that looks like the ones on the left.
Okay.
Yeah. Okay, so any questions about those? So we've got orthogonal and triclinic, we've got regular, we've got sort of shifted regular, and we've got recursive coordinate bisectioning, this tiling idea. Any questions about those partitioning options within LAMMPS? Okay.
I've always kind of wondered, how do you deal with shifting boundary conditions, like in like an NPT simulation? Do you scale the grid, I guess, as you
Yeah. So if let's take this triclinic one, for example, you could be doing an NPT simulation and it could actually be changing, say, the Y size of the box. It could be, if you add the extra tilt dimensions as variables in the NPT, and it can change the tilt a little bit. And so that shifting will actually happen every time step in the NPT algorithm. It's readjusting the box boundaries. But on steps where, once we need to reneighbor, then we decide the new box, we decide where the atoms are, and effectively these partition domains, if the box has grown, then all the lines that are separating the processors, those subdomains have also grown as well. So the bounds of the processor's subdomain will be shifted in accord with the new size or the new shape of the box. So that works both for the tiling case and the orthogonal case, or a triclinic case, I should say.
But so, I mean, bottom line, the NPT algorithm, it converts the positions to fractional coordinates.
Yep.
Then it changes the box and then it goes back.
Yep.
Unless you have a selection that you want to adjust only some of the atom positions. So you can provide a group and then only that group will be scaled along with the cell.
So internally, there's two storages of these subdomains. There's fractional ones which don't change, because it's always a fraction of whatever the current box size is, and then there's the actual coordinates multiplied by the box size, and depending on which of those you need to use, the code keeps both up to date.
And this is also the reason why if you use with the non-orthogonal box, you have more noise because you have multiple steps during the simulation going from real positions to fractional positions and back. Because that's been done as needed because some operations need to be done in fractional coordinates and others or orthogonal coordinates and others don't.
Yeah, the triclinic is the only time you kind of go into this lambda space for scale of 0 to 1 for a regular decomposition where you're not triclinic, then the coordinates are always real, so there's not this swapping back. So that can induce tiny roundoff errors, because the transformation to lambda space and back is perfect. Epsilon roundoff. 70%.
Okay.
Yeah. Okay. So now let's talk about the first communication pattern, which I'm terming regular. And so the idea here, what's going to distinguish these patterns is this next statement. In the regular pattern, processors know exactly who they need to send their data to, what other processors, and they also know what processors are going to be sending them data. So I'll illustrate what this means in practice. So it's a common pattern to use when your simulation domain is spatially partitioned across processors, like I just said. And then typically, if you want nearby information to your subdomain, that means each processor has a handful of neighbor processors, and you're doing short-range exchanges of information with those processors. So here's some example, what's called halo exchange of ghost particles or ghost grid cells. That means you're acquiring as a halo around your little subdomain. You're acquiring copies of other particles or ghosts or grid cells that are on the other processors owned by them. If your calculation is a structured finite difference or finite volume grid, then you think about that halo as like a layer of cells around yours. You might extend 1 or 2 cells depending on the size of the finite difference stencil. And in 3D, it would be like slabs of neighboring cells from nearby processors that own those cells. For an unstructured finite element grid, then it's really just the topological neighbors of the finite elements that you own in your subdomain. So maybe again, you need 1 or 2 hops away in a finite element sense, but you can enumerate, kind of walk that finite element grid, and you can figure out who those elements are and what processors own, exchange that information. So why are ghost particles or cells needed? Anyone want to offer an answer to that question? Please.
That communication efficiency, so that each processor can compute the energies and forces of its owned atoms without exchanging owned information with other processors.
Yeah, it's back to that motivation I talked about in the first slide. You nailed it. You want to do this communication, get these ghost atoms. So now when you have this big chunk, this compute kernel, it's a big chunk. You can compute all the forces between your own atom and these ghost atoms, and do that uninterrupted by more communication. Okay, and it's the same thing with finite difference or finite element codes. If you're going to do these stencil operations, you want to be able to do them for all your own cells, but have the ghost information for where the stencil goes. So just do that in a big loop over all your cells. Okay, so let's talk about this regular pattern for a structured decomposition for this vanilla case. So I just have a box with an orthogonal box with a regular grid. Now I've added this green dotted line around this processor here, and it's the cutoff length of these pairwise interactions or many-body interactions. And so I need ghost atoms from that green rectangle that overlaps. In this case, in 2D with 8 processors, if it were a box around my 3D decomposition, it would overlap with 26 other processors. So I've now exploded this diagram. So I've taken this as processor 0 here, and I've drawn it here with this dark line, and it's 4 neighbors, ones it overlaps the most with, and X and Y are processors 1 through 4. So as I said, the green dash box is the cutoff. But what I need to do is get atoms from those other processors. So I've drawn here in red shade and blue shade the atoms that those other processors need and own, which they need to send to processor 0 so that it has ghost atoms, this expanded box, dotted box around its domain. And so typically we do this in LAMMPS. Well, let me just say conceptually, you can see the way this dotted box is drawn. You potentially would need, if I drew in the other corner processors, so there were 8 neighbors, you would need atoms from 8 different processors to come to you. And that would fill in the ones that are along these edges, and it would also fill in these 4 corners that are drawn in dark blue. But what LAMMPS does is an option to do in 2D. Instead of exchanging information with 8 neighbors, it exchanges only with 4. And in 3D, it would be 6 neighbors instead of 26. And this diagram kind of indicates how it's done. So initially, there's exchanges in the X direction. And so processors 2 and 1 are sending this layer of grid cells on the right or left side of their domain and sending them to processor 0. That allows processor 0 to fill this in. But now if you think about what processor 0 would pass to processor 3 instead of the other way around, it now owns atoms that are some ghost atoms that need to go down to the processor below. And so 4 and 3 also received atoms in the X direction that allow them to pass these little extra layers on the left and right of their domain, and they can pass that as one message that it contains owned and ghost atoms on that processor down to processor 0. And so that fills in the corners up here and the corners down here by talking to processors 4. So again, in 3D, then you would pass up again new ghost atoms that got received in both types of communication, and you would be doing 6 exchanges. So LAMMPS chooses to do the 4 and 6 for these regular domains because we've typically found it faster, at least on CPUs. We're actually experimenting on GPUs to see if doing the corner communication a different way by just directly with the processors might be faster for GPUs. So any questions about that? Did that make sense? Okay. The key point is all the processors are actually doing this simultaneously. So I've just shown what processor 0 is receiving, but all the processors are doing the same thing with their neighbors. So when these 4 exchanges or 6 exchanges are done, every processor has all its ghost steps. And the MPI calls for this are simple I receives, posting receives, simple MPI sends, and then a wait to make sure each of your data has got that. In particular, wait between the X direction and the Y direction, so ensure that you have your extra ghost atoms that you can send some of the processors. Okay, so the very same regular pattern is used for shifted grid boxes like this, where now the grid is still topologically 4 by 4, but the lines have changed, and you just need to figure out which little layers on each of your sides you're going to show. And if actually the cutoff is quite long and it extends out to multiple processors in another direction, there's actually just more passes of that left-right communication that's done to acquire atoms effectively further away processors. And if it's a triclinic box, it's again the little same regions, the same topology, but now it's just a tilted set of atoms that you're passing between your neighbors. Again, you're doing just the 4 exchanges instead of 8, and 6 instead of 26. Okay, so how does it work for these tile decompositions? Well, here I've shown a late snapshot. So I'll show you the movie of a little later where water has collapsed over a dam. This is an SPH model. Actually, we were talking about SPH models yesterday. And so these purple ones are fixed atoms that are the dam. It's initially a column of water that kind of collapses and flows up over this dam. And now here it's hit the right wall, kind of splatted against a layer of atoms that you can't quite see that are a fixed wall. And so here's the partitioning for the load balance, give equal numbers of particles on each processor at this later time step. So I'm going to zoom in on this one processor here. Here's this green region around it where I need those neighboring processors. And so then in this case, processor 0 has 6 neighbors that fall in some of those atoms that are in this layer that's surrounded. And so now we do the exact same thing as before. It's just a little more complicated to figure out. So first we do an X exchange, and processor 0 is going to receive atoms from processor 1. And now actually from 2 processors here to fill in that right edge of ghost atoms that it needs. But in the same way as before, once you've received those from X atoms, that means these 3 processors, 4, 5, and 6, actually have some ghost atoms that it knows processor 0 is going to need. And so it's going to pass those along to fill in the corners for processor 0. So really the same regular pattern of decomposition, except now it's not just always pairwise exchanges. You might need data from 6 processors. You might be sending data back to 6 processors. So I think I've explained all this. As I said, each processor may now do an exchange with a different number of neighbors than another processor, depending on how many processors in this tiling surround it. But it's the same 2 options for acquiring atoms from corner neighbors, and LAMMPS does the one that's shown here. But one question you may now be asking, when you do this decomposition, really a processor in general is just going to know about its box. It doesn't know anything about where the other processors are. There are other places in the simulation. Depending how you recurse down this tree, the processors who are actually close to you could be really any set of processors, and you don't know easily who those are. So in the regular grid case, we just number the processors 1, 2, 3, 4, 5, 6, 7, 8, and we know that it's a 4x4 grid, so we know exactly with trivial computation that my neighbors are 5 and 1 or something like that. So how do we do that for RCB? So that's the question I'm going to answer on this slide. How does each processor know who its neighbors are in this title? And this is one of the nice things about RCB, that it's actually fairly easy to figure out. And I'm going to explain this to you. So here's a little zoom in of that snapshot where I have this processor here with its green box, and these are the 6 neighbors around it that I showed before. So remember, to do regular communication, I have to know who to send to and who to receive from. So how do I figure that out for this irregular or for this tiling approach with RCB? Well, if you think about it, the RCB decomposition is defined by P, where P is the number of processors, P minus 1 cuts. If you're on 2 processors, you only need to make a single cut, and you know where that cut is, and you know who's on the left and right. If you have 4 processors, you make that first cut, and then the 2 each do 1, so that's 3 cuts. If you recurse down to however many processors, it's always P minus 1 cuts. So you can store all the information that's needed about that cut in a geometric sense as simply the dimension, X, Y, or Z, that it was made in, and the position in that dimension where the cut was. So what we do, as soon as the decomposition is made by the load balancing operation, every processor knows one of those cuts, and we do a little altogether to store that P-link vector on every processor. It now knows all P minus 1 cuts in the order of the recursion. And so this only has to happen once when load balancing is performed, say every 1,000 steps or something like that. Even if you're on a 1,000,000 MPI task, that's only a 1,000,000 link vector, which is not much memory. And so you can really store in a compact form all the information about this geometric composition. So when you have that, what we do is we take this green box, which represents me plus my cutoff extent. We drop that green box on this tree of cuts, and we recurse it down to find the 7 processors that it overlaps with. So the way that works is we drop it first on the very first cut, kind of the root of the tree. And if the box doesn't straddle the cut, it's somewhere over here, then we just leave the box as is. But if the box straddles that first cut, we basically partition it into 2 boxes. And then we continue down, and most of the time we won't be cutting the box, but we keep cutting it. And when it gets to the bottom of that tree, it will have been cut into little boxes that represent its overlap with each one of these 7 processors, including yourself. So that one we can discard because we don't need to communicate with yourself, but we know out of the 7 that 6 of those boxes are going to be its neighbors. We'll know the processor ID by the place in the P-link vector, and we'll know exactly what overlap we have with those processors. So that allows us to set up that little regular pattern of communication I talked about. All the processors do this simultaneously to figure out their neighbors. Then they know who they're gonna send from or send to, or who they're gonna receive from. So again, key point, this may seem like a complicated operation, but it's really very quick. And it only needs to be done once each time the load balance or the partitioning changes. Okay, any questions about that? Does it make sense? If you see a few puzzle looks, go
Does
ahead.
this capture, because like in the diagram, you can see how in the bottom left where the blue atoms are.
Yeah.
Right, that's within the green box, but it's not an actual adjacent processor grid, right? So does this algorithm catch, if you're,
Yeah.
right, do you see what I'm saying? Like,
Let me
goes,
go back to my previous diagram. Yeah, I actually, now I'm seeing that one was here too. But
Right,
I
because-
didn't actually include it in this diagram.
Right,
It
but
could have,
for-
it could have been, there would have been a little one here. So
Okay.
yes, it does actually capture it.
right,
So I
okay,
guess.
so
in
it's
the-
captured
I
there then
guess-
still.
Yeah, so 1,
Okay.
2, 3, 4, 5, yeah, so there's actually 8 processors that you'll, have to take yourself out, there's actually 7.
Okay,
They
yeah,
would need to communicate with. But yeah, because that is a processor that you're gonna need to effectively get atoms from in order to have the ghost atoms.
right, but it's covered from the X portion still, right? Because the processor flow will grab and left.
I think it actually would be done, I think it actually, well, it would be done in the Y, because this processor would get them, and then it
Oh,
would
right,
pass
right.
them up when it does it in the Y. Yep, that's a good point, I hadn't noticed that, my diagram didn't quite match what I put on the slide. Yeah, but it does cover that.
Right.
Yep, and there could, in fact, there could be, multiple, if this was really dense with atoms, there could be multiple of those processors here that were just anywhere covered by that green box in a geometric sense, it's gonna find them. Yep. Okay. Got it covered that. Any questions? That's my last slide on this regular communication pattern for all the different kinds of spatial partitioning in LAMMPS stuff.
So is there any way to overlap communication with work? Like, I know we don't do it in LAMPS, but could we start, computing forces as soon as the data comes in instead of waiting for everything?
Yeah, so this is the communication pattern, as I'll talk about later, that's used to acquire ghost atoms right before you do forces. That's what you're hinting at. And so in principle, if I go back to this diagram, in principle, I could overlap work by, sorry, it's not going to work if I point there for people on Zoom. I could do work in the interior of my domain with between owned atoms, basically, before I need the ghost atoms to do the owned ghost interaction. So if we partition the force routine and the loop over neighbor list into kind of owned work versus owned ghost work, we might be able to do some of that overlap. That would be fairly major restructuring of either the neighbor list or the force method, compute methods in pair styles to do that. And it might be fairly simple for pair styles, but it would be more complex for many body types. Okay, any other questions about regular communication? Okay, let's talk about the second pattern, irregular. So now processors know who they need to send data to, but they don't know who's going to send them data. They don't know who they are. They don't know how much data they're going to send them. So typically, as I'll show you, this is well, it can be that we need to send data to an arbitrary set of processors, but usually it's a smallish set of processors that need my data. And likewise, they're going to be sent, some small number of processors, might be different processors, are going to be sending me data, but that's what I don't know. So here's some examples. After you do a load rebalancing, you need to send, you created one of these new partitionings that I show, you have to get data from the old owners of those atoms to the new owners of those atoms. And every processor knows where their atoms need to go, but the new processors don't know in the old decomposition which processors are going to be sending data. Another one is the transpose of an FFT grid, the swap dimensions. So I'll talk in more details about all of these later. But you need to transpose the data so you can go from, say, X pencils on each processor, so you can do entire 1D FFTs in X, to having entire Y dimension on the processor, so you can do Y dimensional 1D FFTs. And then there's the long range movement of particles to new owning processors, which can happen with various commands. LAMMPS. Typically not in the middle of a running simulation, but maybe between simulations, you do things that morph the system in a way that atoms move a long distance, and we need some way to ensure those particles get to those processors. So in all these examples, and again, I'll talk more about these actually in the second talk, the sending processor knows where to send its data, which in this case would be its atoms. It just doesn't know the inverse, who's going to be sent. And that means unless you know that, you can't really write the MPI communication with the sends and receives. So other packages I know of, like linear solver packages, Trilinos and Petsy, which maybe some of you have heard of or used. They're great giant packages. A lot of their focus is on sparse matrix solvers of different kinds. They typically need to set up these kind of communication patterns where they may know who they're going to send to, but not who they're going to receive from. There's a large package called Zoltan, which implements a variety of load balancing techniques, both for particles and for grid-based or unstructured finite element grids. So RCB is just one of the things it uses, but a lot of these load balancing cases are exactly what I described there in the third bullet, where the load balancing is defined, but now we have to get the data where it goes, and processors don't know what they're going to receive. So let me just illustrate what the issue is with RCB. So on the left is an old decomposition with the black lines on 12 processors. I'll talk about this little red rectangle in a moment. On the right is, say, after the balancing, a new decomposition on 12 processors shown with the red boxes. And remember, because of the order you make these cuts and how you decide which dimension of where the particles are, what used to be processor 3 over here could end up to be processor 3 up in the other corner in a different one. So what I've shown superposed here is a particular processor here in this shaded box. In the new decomposition, this is what it overlays in the old decomposition. So if you think about it, for this new processor, what it needs to know is that it's going to receive data from these 5 processors that red box overlaps. So all of these processors, this processor knows it's going to send data, some of its data to that red shaded processor. The other ones know that as well. But if you're just in the new decomposition here, this processor has no idea who it's going to receive that data from, or even how many processors are going to send. That's the issue. So the load balance operation, typically what it returns is you have a set of owned atoms, and it's going to flag each one with a new processor that it needs to go to. So that's why you know the send part, but not the receive part. Okay, so now we're going to answer this question. How does the red shaded processor know which processors on the left are going to send data and how many atoms they need to send? Okay, so there's an MPI call, which maybe you've heard of, maybe you've used before in other contexts. It's called MPI reduce scatter, which solves exactly this problem. And it's one of the kernels of this irregular communication that I'm talking about. So what each processor does is store temporarily a p-length vector that's as long as the number of processors. And here I'm just numbering the processors 1 to p. So each one allocates a processor vector that's of length p and initializes it with zeros. And then what it does is loop over its atoms and say, I need to send some atoms to the processor. If this was 1, 2, 3, 4, I need to send some atoms to processor 2. I need to send some to processor 4, 5, 17, 23, whoever it needs to send to. All the processors do that. These vectors, a p-length vector from every processor, is the input to the MPI reduce scatter. And the reduce is that it's going to, in MPI, under the hood in this MPI call, it's going to reduce these vectors so that the output is a single value per processor that has the scattered information for that one location in the vector. So for processor 17, it would be the 17th value in all of these vectors summed up to a number. So in this case, it would mean processor 17 was flagged by all the other processors as a sendee as they were being sent to by all the other processors 5 times in those other vectors. So that reduce, you can choose different reduce operations. We would be doing a sum in this case. And so that it means every processor gets the exact number of processors that are going to send data if you set the vectors up this way. That makes sense? Okay, so that's the key piece of information. We need to break the irregular into something that can now become regular. Once you've received this count, 5 in this case for processor 17, you can do a little construct here to just loop over the number of receives and post a receive for an integer size, a single value that you want. Then all the processors do a little loop over who they're sending to, and they send it the size of the data or the number of atoms they're going to send that processor. And you wait on all these end receive sizes, and now you know exactly how many atoms each of those 5 processors are going to send me, and you can allocate ghost atom data, for example, in LAMMPS to make sure you can store that data when it comes in. So after that's done, you can now do the atom communication nearly the same way as the regular pattern. You know who you're going to send to, you know who you're going to receive from. And the difference is, and I'll show you this later in code, you can't just do exchanges where you post one message, receive one message. You have to post all your receives, and you have to do all your sends, wait on all of the receives to come in, but now you've received all those ghost atoms from another process.
So Steve, in this case, you still don't know who's sending to you, but you know how many people are sending, and then you can just post that number of receives, and they come from anybody, or?
Yeah. So that's actually a good point, which I did in detail here. So you post so many receives, and for each of them, you post it with an arbitrary source.
Yeah.
So the first time you receive in this first little loop, you're going to know the 5 processors. You'll receive that data with the message that comes in, but they could come in any order. So this is again
Is it
kind
just
of,
the count or the actual range?
well, you know both the count from that processor, but you can also ask which processor sent you that
Okay,
message. So that's a detail I didn't put in.
uh,
So this is again kind of all the setup. This would be typically done in LAMMPS when you do a reneighboring and or a load balancing, and you have a new set of information that's coming in. But once you know that, it's going to be fixed for a while, and so now you have exactly the processors, you have exactly the size of the datums. Just use that as a regular pattern for many times.
okay.
Yeah, very good question. I overlooked that detail. So the difference here is before we were just waiting on a single message, but now you have to wait on all the receives because you aren't pairing up with the same people sending you that you're receiving from. Okay, any questions about this irregular communication pattern? Okay, let's talk about the third one, which I call a rendezvous pattern, and I've worked on this with other people that I'll credit at the end. So this is a name we chose for a reason that will hopefully become clear in a minute. So now the paradigm is that the processors don't know who to send their data to. They know somebody needs it, but they don't know who. And they also don't know who they need to receive data from. So that probably sounds like an impossible task, but I'll explain what it means. So typically now we're sending data to a subset of other processors, but it could be nearly all processors that need some information that only I know. And I'm also going to receive data from another arbitrary set of processors, and it could be even all the processors that I need to know. So here's some examples, again, in the LAMMPS context. And these won't make a lot of sense now, but I'm going to explain them in detail in the second talk. So I just want to motivate them here, or the rendezvous idea here. So one is that we need to initialize the properties of a large set of rigid bodies. And we don't know each atom. All it knows is the ID of the body it's in, but it doesn't know anything about how many other atoms are in the body. It doesn't know where they are, by what processors. And so we need to somehow do the communication to get that information figured out. Another is to walk the bond topology of large molecules. So you want each processor to know who are my first neighbors, who are my second neighbors, my third, fourth, fifth neighbors. For some force fields, you need to walk out in the bond topology and be able to enumerate that. And then another example is rerunning a prior simulation, not in a time stepping sense, but reading a series of dump snapshots that a previous simulation created. And when you do that and read them in, the data is not anywhere near where it needs to be, new decomposition. So often these are kind of, especially the first two, these are sort of one-time or setup operations, so we can afford to do more communication. This rendezvous pattern is going to be more expensive than irregular or regular that I just talked about, but we still want to do it efficiently to get things where it needs to be as quickly as possible to do the setup for the enumeration. So again, these descriptions probably seem way too abstract, but I hope by the end of the morning you'll have a concrete idea of how these work. And in particular, I'll explain these 3 examples in detail. So the key idea for this rendezvous pattern is we don't know who to send to, we don't know who to receive from, But what we're gonna do is create intermediate decomposition. We're gonna call it the rendezvous decomposition. And in that decomposition, we do know who to send the data to and what they're gonna use it for. And then the rendezvous processors, once they get the data they need, they're gonna be able to do the computation and they're gonna be able to send the answers back to the processors who need the result. Again, kind of abstract, but hopefully it'll make sense. So again, this intermediate decomposition, it may mean you need to send data to almost all the processors. It's really the same processors, but all the processors in this alternate decomposition, or just a few. And the communication, as you're going to see, is really two passes. If it's really all the processors, you would use MPI all-to-all calls, which are nicely packaged up. But if it's each one sending to just a few, then we can maybe use our irregular pattern. Now we know who to send to in that decomposition. We can invert that, set up the irregular communication, and get it back. And that's going to be sandwiched around a computation that gets done by all the processors in this rendezvous decomposition. Okay, so another thing that you'll see in some of the examples I show is that sometimes if a decomposition sounds like a complicated thing, you're thinking of some spatial way to partition the work, but it can just be kind of a random decomposition of the work where you have some idea associated with the work and you hash it or do something other kind of random just to get a subset of data to a subset of processors. And that can be effective if all the processor is involved because you can effectively load balance the computation and the communication. So why is all of this called a rendezvous pattern? It's because data are all called datums, thinking of a little piece of information, maybe about an atom. Datums are rendezvousing at one processor in this rendezvous decomposition. It needs all of those datums in order to do a computation. Like in the case of the rigid bodies, the rendezvous is going to be based on the ID of the molecule that it's in. And so if all the atoms, all the processors that own atoms in that molecule send all of the datum information about those atoms to one processor, then that processor is going to know all the atoms in the molecule to do the setup that I talked about. So each rendezvous then processor, once it's received all these messages, can perform a subset of the total computations. So it has all the data on a subset. Multiple computations like multiple rigid bodies, and it has to figure out which datum goes with which body, but using a subset of its datums computation. Okay, so here is a motivating example, and this is kind of the last big thing I'm going to talk about in the first talk. So this is not with LAMMPS, it's with a finite element kind of calculation, but I'm just going to conceptually explain it, and I think you'll understand what the rendezvous algorithm and the rendezvous pattern does. So imagine you're simulating a little 2D plate with little finite elements here, and the plate has two holes. So it's a flat plate. And in the physics of what you're trying to model, one of the plate, maybe these are little posts that go through the plate, and through the small one, the plate is kind of torqued through this. There's some stress that's induced in the metal plate that's around it. And so in order to solve the PDE for the stress strain equations, you need to refine the mesh so that where the stress gradients are the largest, you have the finest mesh. So here I'm showing maybe a later snapshot where the grid has been refined around that smaller hole. And then the other hole, let's say it's a heat source that the post through that gets hot, it induces a temperature gradient in the plate. So likewise, to solve the heat equation, solve for those temperatures, you're going to need fine grid around the bigger hole. And so think of these two PDEs for stress, strain, and temperature as being coupled, and you want to do this coupled kind of simulation with two effects being modeled simultaneously. So what I've shown, I don't know if you've seen how finite element grids are typically partitioned by load balancers, but basically they assign a subset of elements to each processor, and those elements are clustered together. So I've kind of shown that in an idealized way by saying, let's say there's a red processor here in the left grid that has a little cluster of grid cells that happen to be near that left hole. And likewise, there's another processor in the right grid which owns a set of finite elements that are kind of clustered together. Obviously, the boundary can be kind of irregular, but they're clustered together around that larger. So if you want to run both the solution to the heat equation and the solution to the stress strain equation efficiently, using other things as source terms from the other fields, then what you need to do is refine and decompose those grids separately in your coupled simulation. So that's why I've shown them this way. But that allows you to solve the physics efficiently because each grid is refined where that physics is important. And then if you partition it equally, that one grid on processors one way and the other grid a different way on the processors, so they have equal number of elements, for example, then you also get efficient solutions to those two equations. So the idea is because you're decomposing them independently and partitioning them differently and refining them differently, that means each single processor is going to own some cells in both decompositions, but those are completely independent of each other. It knows the grid cells it owns, but they have no connection geometrically. So each processor effectively knows nothing about what cells the other processors own in those both decompositions of the two grids. Okay, so here's the coupling for a single time step. We would solve the heat, TDE, for temperature with stress as a source, because that might affect the temperature, and you would get some temperatures. Now you need to interpolate those temperatures on the temperature grid to the cells that are on the stress grid so that each stress cell knows temperature, say, at its corner points. That's both a geometric interpretation, but then you have to map those points, which don't snap up, and get temperatures at the corner points of the grid cell. So then you can solve the stress PDE with temperature as a source, and then you have to go back the other way for the next time step, which is interpolate those stresses back to the temperature grid. So that's two interpolation operations, and geometrically what we need, if we're in this red domain in the stress grid, we need T values from the grid over on the right that are near the cells that are in that little red oval. And vice versa, we need stress values near the little temperature grid cells that are in the green oval. And so, again, the questions are which processors own those values? We don't know because that's totally somewhere else in the decomposition. It isn't anywhere near us. We don't know who to request or receive that information from. We don't even know who to send. So that's the motivation for using a rendezvous algorithm. So here's a very simple pattern that you can think of as like a brute force rendezvous algorithm, and that's to use what you could call a ring pattern. So I'm just showing 4 processors here, but imagine this is a loop arrayed as a ring with all P processors. So it could be 100 processors, 1,000 processors. And what's going to happen in this case is each processor owns, this is from the perspective of the temperature grid, each processor owns in its little green box a set of cells in the temperature grid. But what we're going to, initially, it also owns some cells in the stress grid. What it's going to do is pass those stress cells around the ring so that once you've done P steps, every set of stress cells has passed by my processor. I can look at those and I can pull out the ones that are geometrically close to my T cells, keep those values for the grid points, the geometry of those cells. And once I've done the ring communication that's gone all the way around, I know all the cells that are close to my T cells, and now I can do the interpolation. I can find which ones overlap which cells. I can do the mathematics to take a set of S corner points and map them and interpolate them to a T corner. Okay, does that make sense conceptually? So I'm going to circulate my stress cells around the ring to all processors. P steps of communication. Every processor sees all the S grid cells, and it can keep information about the ones. So the T cells are not communicated in this context. Each receive, I just keep some S cells that overlap my T cells. After P steps, I have everything, and I can do the interpolation. So my question is, what's the computational scale of this algorithm? Let's say I have N grid cells in each grid, and I have P processors. Stuff you thinking about. So each processor, how many cells does it have to look at?
-1.
What's that?
-1.
For each processor, you know, one of these locations on this ring, how many stress cells, the red boxes, how many total cells does it have to look at? Find the ones closest to its T cell.
It's all P, right? Because it looks at each one once, right?
It looks at each message once. There's N over P in each message, but how many messages? Okay? There's N. Every processor has to look at all the grid cells in the stress grid in order to find the ones that are close to its grid cell. And the interpolation itself is with a small set of S cells, a small set of T cells, but I first have to look at all the cells that came to me in that range. So what's the communication cost for scaling this operation, again, in terms of N? How much information is communicated, sent and received by each processor? Yeah, it's also N. Each message size is N over P, but there's P stages of shipping those around the ring. So I'm going to receive N information, I'm going to send N information, every processor. Okay, so you can imagine as N grows huge, this is not going to scale. This interpolation operation is going to dominate the actual finite element solves, which are more like N over stencil operations locally. So that's the problem with the ring algorithm. Okay, so simple, and actually, if the interpolation were something that didn't need to be done every step, maybe it was an occasional setup operation. If you had modest size N or modest size P, this would be okay, but not at scale. Okay, so here's the rendezvous solution. Let's imagine for both of these grids, we're going to overlay a different kind of decomposition, and it's just going to be a regular grid. So in this case, we're going to decompose it into 12 processors. Each processor stores, again, it's green or red ovals, but conceptually there's this third decomposition, which is the overlay grid. So how does that help you? Well, note that in this case, the rendezvous grid is a regular. And what's important is that processors effectively imagine that in this blue grid, in this rendezvous grid, we're going to own, and for the purpose of this interpolation operation, this processor, sorry, I should be using mouse. This processor at the upper right, it's here in both these grids. This processor is going to own these grid cells in the stress grid, and it's also going to own these grid cells temporarily in the temperature grid. So it's important to understand that all processors, we've defined this third decomposition, are going to own grid cells somewhere in the simulation for each of those decompositions. It's the same set of processors. They just own different things. So the first step would be for the S and T processors to each send their grid cell information, geometry of their grid cell, the corner points and the values on it. Send that information to the processor in the R decomposition. So if you're this little red processor here, you know for each of your grid cells which blue cell that falls in. So you can send your blue cells to this processor in the decomposition, and you can send some of them to this processor. I've drawn this so it overlaps 2 of the blue cells. Likewise, for the green one here, it overlaps 2 of the cells. After that stage is done, what this processor owns, this upper right processor in the blue decomposition, the rendezvous decomposition, it owns both S and T cells that overlap that same region. And it received them from arbitrary processors that we aren't showing, because we don't know the decomposition of those red and green grids. Okay, so now the rendezvous processors, they can perform the stress to temperature or temperature to stress interpolation, because they have a group of grid cells that overlap each other. They can figure out which corner points are near which corner points. That uses the grid geometry and both the grid values on that, the stresses or the temperatures can be used to interpolate points on the other grid. But now what's required is those R processors send those interpolation results back to either the S or the T grid to those processors saying, hey, I had some of your corner points, here's the values that now exist on those corner points. So messages would go back if you were interpolating onto the stress grid. These two rendezvous processors send information back to this red processor saying, here's some new values for your point. So all the computation for the interpolation is within the rendezvous decomposition, and here I'm really showing 3 sets of irregular communication, because the red is sending to the blue, the green is sending to the blue, and then the blue is sending back either the red, depending on which interpolation. Okay, so this is sort of the full flavor of the rendezvous algorithm, and it's necessary when the grids have just adapted, because now you have this unknown information about, how to do the interpolation. So you would do this, but once, if the grids only adapt every 100 steps or 1,000 steps, then you could save these little patterns of who I'm sending to, who I'm receiving from, and do irregular or regular or even regular communication on the intermediate steps. So this more expensive operation is only necessary when the grid decompositions. Okay, does that kind of make sense, everybody? Okay, here's my follow-up question. So what's the scaling of both of the computation and the scaling of communication in this new algorithm?
Log in.
Not quite. Close. Again, we have n elements per grid and p processors.
And over P.
N over p. So again, I only have to send my data, and I figured out who to send it to, and I have to send, there's 2 or 3 times that this sending happens, but that's pre-factored in the N over P. The amount of data that's going from each processor is N over P, the amount it's received is N over P. Roughly. I mean, these are approximate, it kind of depend on the actual decompositions. N over P is very different than N, especially if you have 1,000 processors or 10,000 processors. That's the point, that this can now be a fairly load balanced algorithm. And it should be competitive with the other costs, which is like solving the stress equation or solving the heat equation, because those should also be N over P in the partitioning of the group. So now, hopefully the entire algorithm, we do this extra kind of fancy communication, but it scales well, and it should help the whole thing run. Okay, so questions about that? I've described both rendezvous and ring patterns. Did they make sense in this context? Is there something you want to ask a question about? Okay. All right. Well, my last quiz question for this talk is I've shown the diagrams. Does somebody want to try to explain back the rendezvous algorithm for these 3D compositions? Don't want to, that's fine. Is it clear enough in your head how this works to make sense of it?
I mean, you just basically make a third grid, right? And then
Yeah.
you just use that to pass the
Yeah,
information
a third,
to the other.
I think of it, yeah, it's a third grid, but it's a third partitioning of the
Yeah.
grid cells across spots. I should have actually showed for these green and red the kind of partitionings that a load balancer would do for refined grids like this, because you just get these little irregular patches of clustered grid cells, but it would be very small patches over here and very big patches over here geometrically because of the coarseness of the grids or the refinement of grids. Okay. All right. With that, any further questions on the first topic? Otherwise, we'll take a break. Okay. So here's the outline again. I've just done number 1, tried to tell you about these 4 different patterns and illustrate them at least enough that you have a basic understanding. In the second talk, I'm going to talk specifically about how these patterns are used in places in LAMMPS, illustrate them in another code as well, and ask a couple more questions about, I think the rendezvous pattern is sort of conceptually the funnest to think about. Ask you a couple questions about how you would use a rendezvous algorithm to tackle that problem. And then I'll give you a few code level implementation details within LAMMPS to illustrate it. Okay, and let's take a break. It says 10:05. Axel, what time do you want to come back?
20 after, so 15 minutes.
Okay. So.
You have to share.
Okay, are there people still on? There's nobody on. I'll feel a little more mobile to walk around the plane.
So 6 people.
Okay, all right, well, I'll do it just like first. Okay, like it's showing like you expect.
Yeah.
Okay. All right, well, welcome back from the break. This is the second part of my morning presentation. And it's a little longer than the first one, but I think I should still comfortably be done by noon, maybe an hour, I'll talk an hour and a half at most. Still have time for questions or comments, so it should be good for lunch. Okay, okay, so this is my overall outline. So in the previous talk, just a few minutes ago, I was talking about topic 1, these 4 forms of communication patterns that we discussed. Now I'm going to dive in a little more detail, show you how these patterns are actually used in LAMMPS, give you other uses of the rendezvous pattern in other kinds of HPC applications, both simulations and analysis, and then give you some code level implementation details in LAMMPS as well, that hopefully will be put some meat on the bones as far as how this is actually done. So let's start with how LAMMPS uses the regular communication pattern. So recall that the signature of this pattern is that each processor knows who it needs to send to, knows who it's going to receive stuff from. So also recall that each processor stores 2 kinds of atoms. Within its little geometric subdomain, it stores owned atoms that are uniquely owned by that processor, and it stores ghost atoms, which are copies really of atoms that are owned by other processors, geometric sense that are nearby processors. So here's the loop, or basic loop over time steps in a standard MD simulation. This is the way LAMMPS and many other codes does it. One wrinkle that might be a little unique to LAMMPS is it's a velocity relay algorithm. And so that means the updates of velocities are split across 2 points in the time step. So think of the first operation. If you have current forces, the first operation is to update the coordinates by a full time step, update the velocities by a half step using those forces. Now that the coordinates have been updated, that's we need to acquire new ghost coordinates for ghost atoms from the other processors. And once we have that, as we talked about briefly, each processor can compute forces. There's no communication needed during that computation unless it's something like an many-body potential that we'll come to in a moment. But you're computing interactions between pairs or multiple many-body effects between owned atoms and also owned and ghost atoms. Now, typically that will compute forces, and forces will be put back both on the owned atom and ghost atoms. So there's now another communication step that's needed to sum those forces that are existing on the ghost atoms back to the processors that own those atoms so they can get the total force on each atom. And then at the end, that allows the total force, new force allows the second half of the time step updating those velocities. And we're ready to continue for another step. Okay, so the velocity relay part of it, if you're not familiar, the forces are the velocities are kind of at the half step where the forces are computed, but that even allows consistent computation of forces that depend on velocities, like the granular systems, where there's both velocities and velocities of a pair of particles and their coordinates contribute to the force that's computed. Okay, so both steps 2 and 4, the ones that are highlighted there in red, acquiring ghosts and summing forces, those are both done via this regular communication operation I've described with LAMMPS. As I said, the ghost atoms are needed for the force computation, and the summed forces are needed to get the total force on the atoms, which is used in a variety of contexts by other parts of the time step. So LAMMPS distinguishes between those two computations with what's called forward communication and reverse communication. Stan mentioned this briefly yesterday. So the idea of forward communication is when I want to send owned atom info to other processors to store with their ghost atoms. Okay, so here I showed this diagram before, but I'm just going to go through these stages to make sure it's kind of clear in your mind how forward works, and then I'm going to contrast it with reverse communication on the next slide. So in the X dimension, processor 0 is the one that's receiving owned atoms. In the X dimension, processors 1 and 2 send information to processor 0. And then in the Y dimension, processors 3 and 4 send information to processor 0 up and down, so that it acquires all the atoms, including its corners. And again, the idea is that all the processors are doing this simultaneously all across the grid of processors, and so everybody receives their ghost atoms. So reverse communication is, as you might imagine, the inverse. Now, ghost atom information is going to be sent by each processor back to the processors which own that atom, and typically that information is summed, like in the case of forces, back to the owned atoms. So on the left is the diagram I just showed you, and I showed you a couple times for the forward communication. The diagram on the right looks exactly the same, but there's two differences I want to highlight. One is that the directions of all the little black arrows for who's sending to who are reversed. So in this communication, in this diagram, processor 0 is sending its ghost atom information to these 4 neighbors. And so in order to do that and treat the corners correctly, now instead of doing X first, then Y, now Y needs to be done first, then X. The reason is processor 0 has information on ghost atoms that extend across the domain. It sends those to 4 and 3. So it's sending it some information about atoms that processor 4 owns, but some that are ghost atoms of processor 4. And those forces get summed to either owned atoms or ghost atoms in processor 4. And then in the second stage, the X dimension, processor 0 would be sending just these smaller red slabs to 1 and 2. Those are all owned atoms on 1 and 2. But because processor 0 did some summing before, there might be a quantity there that came from processor 1's corner, which has been summed once by processor 0, and then a second time by processor 2. So that's what I mean by this last bullet here, that the corner processor values can be summed by both ghost and owned atoms. And in 3D, it's, as you might imagine, in forward, we do X, then Y, then Z, but in reverse, we do Z, then Y, then X. All the messages are going in the opposite direction. Okay, so does that kind of make sense what I'm referring to here with owned or forward and reverse communication? Okay, so I've already told you in the time step loop where both the forward and the reverse communication is done, the acquiring of the ghost atom forwards, that's forward communication, and then summing the forces back to the owned atom, that's the reverse communication operation. And the packing of information, the simple case is just coordinates and forces, but depending on the atom style and what other properties might be there, there might be dipole moments or other things that have been updated, or for spherical particles, there might be rotational torques that have been applied. And so those things are summed back as part of the communication as well. It's actually the atom style that defines exactly what information is going to be communicated for forward and reverse communication in the time step. But key point I want to make is these same forward and reverse patterns are used throughout LAMMPS to share owned atom info with ghost atoms and vice versa. So it happens in many pair styles, it happens in many fixed styles, compute styles, it even happens in some bond and dump styles, which I won't get into, but look for those forward and reverse calls to see what's done. So in the pair styles, the example that Stan actually talked about yesterday, the embedded atom method, is kind of one of the simplest many-body potentials, but there's a forward communication that's done to pass actually the derivative information about the embedding function so that forces can be, that has to be communicated to ghost atoms so that Forces can be computed at the very end. And there's a reverse communication earlier in the stage of these density values that are summed on atoms, because those are done pairwise. And basically the full information about each atom's density needs to be passed to ghost atoms. So then there's many body potentials that use the forward and the reverse in different patterns with different information. Often, as in the case of EM, it's internal quantities that got communicated, but that's done in stages. And so the ghost atoms need those properties, and information that got stored with ghost atoms needs to be communicated back to home atoms. So the modified EAM, the cone potential, there's some lubrication potentials. The amoeba force field has many terms that involve this communication, reactive DPD, etc. So for fixed styles, I picked one to tell you a little bit of details about QEQ, which is charge equilibration. It's done in reactive potentials like reacts and comb and others. Basically, the QEQ equation for the charge equilibration is choosing new charges for each atom that satisfy the QEQ equation, and that is like a sparse matrix solve that's done iteratively. And so the QEQ equation sets the constraint and the conditions that need to be set to minimize this quantity of how the charges interact and get a correct charge on each atom. And the sparse matrix is because this information is essentially communicated to ghost atoms back and forth. And if you think of it as a matrix, there's connections, non-zeros in that matrix with owned atoms and ghost atoms. And so the forward and reverse is done each iteration of the sparse matrix vector multiplying, and you have a few iterations to converge the charges to new values. So those forward and reverse operations happen many times per time step. Also happens in shake with Monte Carlo fixes, with orientation forces, where you assign different grain boundary orientations across a grain boundary to different sides of the boundary. Hyperdynamics is something where bias potentials are chosen and applied to different atoms. There's communication that needs to happen there as well. In computes, imagine you're computing the stress per atom. Well, that's done with F.R, but you need to sum up in the reverse effect. In a reverse context, you need to sum these little ghost atom virials that are the virials that have been computed on ghost atoms. You need to sum their effect back to the owned atoms, so that reverse communication happens in that compute style. Similarly, for potential energy per atom, a coordination number per atom, cluster factors per atom tallies, those are done in a way that puts information on ghost atoms that needs to be accumulated back to home atoms for the compute to produce its final output. So what's common to all of these classes, including the atom styles, as I mentioned for these use cases at the top, is the pack and unpack of what data is going to be communicated between ghost atoms and owned atoms. That is decided by the parent class. So each compute or fixed style defines exactly what it needs to pack, puts it into a buffer, and then the forward com or reverse com routine within the com classes just takes those buffers and knows how to do this regular pattern of communication. So this split between who decides what goes in the messages and who knows how to do the communication pattern, I think is a pretty powerful one, because lets any new class in LAMMPS figure out what to send, but we have this black box reverse and forward communication routines that can just shift data around. Okay, so let's talk about another application of regular communication in LAMMPS, and that is what we call distributed grids. So overlaying a grid or a mesh on your simulation domain, especially for a particle code, can be useful in several contexts. So one is just for analysis. Maybe you want to average particle properties over larger subdomains like the overlaid grid. Essentially reduce the amount of data you're using to represent some property that you're measuring. It's also useful in visualization. Maybe you don't want to visualize a billion atoms. You'd rather represent maybe a million grid cells, little chunks of atom information in a way that gives you still a nice picture at that resolution. And then there's a variety of hybrid particle grid models. I think some of us talked a little about these yesterday, where you actually want to express your equations in a way where some properties are stored with the particle, some are stored on the grid, and you alternate between doing computations in both domains. So examples of hybrid particle grid models, the classic one is long-range Coulombics. where the solve, well, it's really in the name of the method, particle mesh implies the use of both mesh and particles. So that's P3M and LAMMPS, but particle mesh DWAL in other MD codes is essentially the same thing. We just have some slight differences. The motivation for this is rather than defining a super long cutoff and trying to do everything pairwise in the pair style, it's much more efficient to let FFTs solve things on the grid in order to get the effect of these long range charges. So what happens is charge is mapped to the grid cells. Talk a little more about that later. We get to the FFT discussion. And Poisson's equation is then solved on the grid via FFTs. That's an efficient way to do it. Once you get back or electric field on the grid points, and those fields need to be interpolated back to individual particles so that you can apply a force to each particle due to the long range Coulomb. Okay, another sort of hybrid grid particle model is called the two-temperature model, which is used in solid state physics. It's the fixed TTM grid command in LAMMPS. You have your normal set of atoms, which you have a peristyle and you're working with in the same way that you normally would. But instead of storing electrons, you want to get the effect of electronic degrees of freedom on things like heat conduction. You store the electron temperature on a grid that overlays the simulation. And so what that means is there's atom properties that put information on that grid, and then you do a finite difference kind of solution on that grid to solve how the heat diffuses around on that grid. You get new temperatures, and then that information is coupled back to the individual atoms to affect their dynamics. And then there's a variety of coarse grain models for coarse grain materials, like the material point method, which use both grids and particles. And so this method is not yet in LAMMPS, but I think it could be conceptually with the kind of support that I'm talking about here for distributed grids. MPM is basically a mesh-free continuum-based material model. And what's stored on the grid are quantities that allow you to compute deformation gradients, which affect the dynamics of the particles. So there's kind of an acceleration vector, a velocity vector that's computed on that grid and is applied to the particles. There's a back and forth between the particles. Okay, so how are distributed grids supported in LAMMPS? Well, it's a regular grid that overlays the entire domain, so they can be a 2D grid or a 3D grid. And so now I'm showing you two diagrams here, which were exactly the same diagrams I showed before, representing processor subdomains. But now think of these as representing a grid, which is 4 by 4 in this case. But it could be a 100 by 100 grid. You could still have the 4 by 4 processor domains, but you could have a 100 by 100 grid superposed in each grid cell, or each processor would own multiple grid cells. So if it's a triclinic domain, then think of this grid that's overlaid as having the same shape as the triclinic box. The grids can be periodic or non-periodic, matching the boundary conditions of the simulation box. And in each dimension, the grid can be any size you want. So I've shown 4 by 4 here for 2D, but if it was a 3D system, you could have 1 billion grid cells, 1,000 cubes. Or you could make it coarser in one dimension and less in another dimension. So it could be 100 by 500 by 3,000. And you can even, essentially for a 3D simulation, collapse it and have grid cells that extend all the way in one or more dimensions. So you could have a 10 by 10 by 1 grid. For example, this left diagram, imagine you're looking at a top face of a cube. So it's a 4 by 4 by 1 grid. And in the Z direction down into the image here, the grid cells are long and skinny and extend all the way down. You could do 1 by 1 by 10, or you could even have a single grid cell that overlaps your entire simulation. That's obviously not very useful in practice. So what do we mean when we say the grids are distributed? Well, the basic idea is simple. Each processor owns grid cells within the grid whose center points are inside its subdomain. So because of the way we've defined subdomains, it's this rectangular tiling, parallelepipeds in 3D. That means each processor essentially owns a subblock of grid cells within the full grid. Just like the partitions are regular, so would the subblocks be regular. And as for reasons I'll talk about here, processors can not only own some grid cells, but they can store ghost grid cells around their domain for reasons for the purpose of its particles to be able to interact. And this works equally well with brick or tiled spatial decomposition. So here's this familiar picture, a snapshot of SPH where we're late in the simulation, and on the left, I'm showing the processor domains. What I've done on the right is overlay a fairly fine grid on that set of processors. It's maybe like 100 by 50 grid, something like that. And now I'm coloring the grid cells based on what processor owns them. And you can see here, for example, that because where the center point lies, depends on where the grid actually is, these colors don't exactly line up with the processor subdomain. So here, processors that were in this, or grid cells that were owned by this pink processor here, those grid cells extend a little bit into the other processor. So that's just naturally the way that grid cells are going to be assigned to one processor. The grid cells have a finite size. So typically, again, the grid cells are smaller than the processor subdomains, but they don't have to be. You could, for example, in 2D, you could partition this with a grid that was 100 in X and just 1 in Y, and the grid cells would be basically long, skinny. Okay, so there's two classes that have been added to LAMMPS fairly recently, Grid 2D and Grid 3D, that offer support for these distributed grids the last few years. And so a pair style, a fix, a compute, or a k-space style like P3M can instantiate instances of these grid classes. And each grid cell can store that the parent, the pair, or the fix decides what information needs to be stored with that grid cell. So on a single geometric grid, the parent can decide, I'm going to store one or more scalars and or one or more vectors for quantities of information on each grid cell. So as I've tried to emphasize, atoms from multiple processors may contribute to a single grid cell. A good example, or two good examples here, is that when you do charge smearing for P3M, you define a particle and you say that's going to affect on the grid, which is going to be used for the FFTs, that's going to affect a stencil that's 5 by 5 by 5. So 125 grid cells get a portion of that charge smeared to it by that single particle. So that clearly means that if it's a particle near the edge of your subdomain, it's going to smear charge onto grid cells that are owned by another processor. Likewise, if you have a grid cell like I showed in the SPH diagram that overlaps two grid cells, even if I want the particle only to affect the grid cell it's in, that means for this grid cell that I own, there's going to be some other processors whose particles contribute information to that grid cell. So what that means is there's a requirement to be able to do forward and reverse communication on these grids. So forward communication in analog with the particles is when owned grid cell data is sent to ghost cells, and reverse is the inverse. Ghost cell information is sent back to the owners of those grid cells. So again, the caller is going to provide pack and unpack methods, the fix or the pair style of the compute that's using a distributed grid, so it can pack exactly the data that it wants to ship in the forward and reverse context of the processor. So these grid classes thus implement, for grids as opposed to particles, they implement the very same regular communication pattern that I talked about in detail for particles. But now it's just for owned and ghost grid cells, not atoms. So it uses the very same MPI calls, I receive, send, and wait, that regular communication does for atoms. Okay. So here I'll just show you a little example. This is the SPH movie again. This is just the particle view of it, with the processor subdomains being reload balanced as it goes along. So kind of remember here, let's see if I can point, the splash happens across this thing and it kind of piles up at the right corner here. I'll show it one last time. Just remember that geometric pattern. So I want to show you in the next. What I've done now is run the exact same simulation, but I've used this fix ab grid, and then I'm going to visualize not the particles, I'm going to visualize grid cells on this finer grid that's overlaid over the processor domain or the simulation domain, and I'm going to color them by the proportional to the density of particles. So in this case, it's the initial snapshot. It's not really showing anything. Oops. But here is just showing color in each grid cell, and hopefully you can see that it's the same geometric pattern where stuff splashes over here, spreads out here. More time. spreads out vertically here at the right wall. But anything that's blue are grid cells that didn't have any particles. Ones that were purple or red had more particles. So that kind of the density is shown for where the fluid is in this kind of plot. So that's very easy to do with these commands and using these grids internally. Okay, any questions? So I've showed you several different ways regular communication is used in LAMMPS. Any questions about any of these examples? Okay,
Other question?
yeah,
So are there any plans to implement MSM into LAMPS
MPM.
or NPM? Yeah.
I've talked a couple times to people who might be interested, but nobody's ever been pulled up and said, I want to do this.
Fair enough.
If there's a volunteer here who wants to. Let me know and we can talk about it. Okay, now I'm going to talk about how LAMMPS uses the irregular communication pattern. So again, remember the signature of that is the processors know who to send information to, but not who to receive it from. And this MPI reduced scatter method is the key MPI method that allows each processor to find out how many processors are going to send it information so it can then accumulate what it needs to do the regular sends, receives, and waits. So the most common use case for irregular communication in LAMMPS is when atoms move so far due to some operation. The regular kind of communication might lose atoms. And in this context, regular communication means the assumption is that atoms only go to an immediate neighbor processor. So they go to the left, right, up, down, forward, back, and one of those processors is going to need that atom. But if things migrate too far beyond one processor away, then atom LAMMPS, and this happens sometimes when you run a simulation with a bad force field or a parameterization, atoms get too close and the system blows up and an atom goes out to infinity or somewhere at the other side of the box, and LAMMPS will give you an error, I've lost atoms, and that's what's happening in this case. And there you might say, well, if I do the irregular communication, which I'm going to talk about next, I could recover that atom and put it in the right place. That's really probably not a good idea because the atom doesn't want to be over here someplace the other side of the simulation box at all times. So an error is safe. So here are 4 commands that can do this kind of operation legitimately of moving atoms long distances. You may not have used these commands, but under the hood, they're using this irregular communication. So one is change box. You have some atoms and you change the box dramatically, maybe the shape or the size. Maybe you're wanting to create some empty space so that you can add new atoms over here. This could be in the setup part of your calculation. But once it's done that, it needs to repartition the domain so that all those atoms that are already there are owned. So when it does that, those atoms can end up on very different processors that are not neighbors in the decomposition. So at the end of its operation with the new box, it does the new partitioning and it uses the irregular communication to get those atoms ready. Displace atoms is another similar one. Now you have a box, you don't change it, but you might want to move a chunk of atoms a long distance in the box. Again, you might generate a crystal initially. Now you want to move half the atoms over here because you're going to put some liquid or something in between them to do a kind of simulation. So the displace atoms command can likewise move things a long distance, so it does irregular communication at the end to make sure atoms get where they need to be. The read restart command. Now you're potentially running a simulation on 10,000 process, for example, writing multiple files, but you're going to read it. Maybe you're going to only restart it on 100 processors. So now you've read in a whole bunch of atoms as quickly as you can to reduce the I/O cost, but they're all stored by completely the wrong processors. And so again, you need some operation that's robust to get those atoms where they need to. It's the irregular. And then the last one is there's 2 external pieces of software, MDI and IPI, which kind of support a client-server mode for different codes to be coupled together. And both of them like to use LAMMPS as an MD engine to compute certain things and let second code or the driver program do different things with what LAMMPS is producing. So there's 2 commands in LAMMPS, MDI_engine and the fix IPI command, which hook to both of these external libraries. And so when you build LAMMPS with those, they're in their own packages, the MDI package or the IPI package, I believe it is, or maybe it's extra. I can't remember really high, big side.
It's an extra fixes.
Yeah, But it knows how, the build knows how to link up against this additional software that LAMMPS needs. Maybe download it onto your box. So there's things that these systems do that just sort of use the regular kind of communication. Maybe you're getting quantum forces and you're doing the normal kind of time stepping in MD. So things aren't moving very far. There's also use cases where these other codes or these drivers pass LAMMPS a set of unrelated configurations, a series of configurations of atoms. So in the MDI context, you might be doing machine learning kind of training or analysis where you have a whole set of conformations and you want LAMMPS to use one of its force fields to compute energies and forces for all those conformations. And so you're just feeding them in as a series of conformations. Those atoms then are going to be very different positions than the previous conformation. IPI likewise might be running a multi-replica simulation like tempering and decide to swap replicas, so it's going to send a new set of atom coordinates to LAMMPS or atoms with different properties that are in totally different positions. It does that. So both those packages or both these commands check if it's not possible to sort of do the normal kind of regular communication to get atoms where they need to be, and they trigger in a regular communication. If that's the case, the confirmation is very different from what it was before. Okay, two more examples that have some nice movies with them. There's a fixed deform command that can shear a simulation box and its atoms, and it can actually shear it continuously, like infinite applied shear. So a use case for a liquid to be measured would be to measure the viscosity of a fluid. And rather than let the box, as you're going to see, this orthogonal box is going to convert to triclinic and tilt over. If you were going to shear it forever, it would become a very long, skinny rectangle, or a kind of a rhombus, which would not be good. So it's the continuous shear is modeled by performing what we call box flips. So I'll show you a little quick movie here. As soon as it tilts far over in one direction, it gets flipped back to a symmetrically identical position on the left, and it keeps doing this time and time again. So you can run that as long as you want, let the flow develop and get very good, accurate viscosity measurements of that fluid. So the box flip itself happens in a single time step. The box flips from here with its decomposition back to here. Some processors are going to own very different atoms than they own in the other direction. So that's after this box flip, or when it happens, that's when this irregular communication pattern is invoked to make sure that things end up where they are. So in this little simulation, I think it flips 3 times, that irregular communication pattern will be invoked 3 times. The last example is our familiar dynamic load balancing. Now I'm going to run this simulation all the way to the end so you can see how the water ends up under the influence of gravity. So here's the column of water initially. It's going to collapse, flow across these 2 dams. There's a little wall here at the left and right side, which you can't really see of stationary atoms. So my point here is after each load balancing, which might be invoked every 100 or 200 steps in the simulation, one of these irregular communications is always invoked. So as I run this simulation, you'll see that during this simulation, load balancing is invoked hundreds or 1,000 times. And each one of those is using that irregular communication to make sure atoms get where they need to. So I don't know a lot about SPH, but I think it's pretty cool to model something macroscopic like water, dams worth of water. These kind of models. Hydrologists might not think it's very accurate model. Still pretty cool. Okay, so again, that's where the irregular comp pattern is used. Okay, one more. Oh, I do have 3 examples of other 3D simulations that require some load balancing to run efficiently. So these are not movies, but pictures that people sent me. This is a coarse grain model, a virus-like coarse grain entity is budding through a membrane, which is also represented in coarse grain fashion. This is an atomistic level model, but these are little hollow struts for a nanoengineering application trying to stress that box and see how strong these little hollow struts are at the nanoscale. And so this box is mostly empty, and that's why using the load balancing can give you an efficient simulation. And here's another coarse grain model, in this case of alpha beta tubulin, kind of unfolding and then spiraling at the top, and it's dynamic how that happens. This is a snapshot showing you why you want something load balanced in order to model that process. So all of these cases are gonna, again, use that irregular communication pattern whenever load balances is invoked. Make sure the atoms are retained, put in the proper place. So the collaborators, they're not my collaborators, these are just people I knew that kindly sent me their images, John Bryan, Stokowski, Jonathan Bollinger, different folks that use LAMMPS for these kind of things. Okay, one more irregular communication pattern I wanted to mention to you, and that's to return this long-range Coulombic solver with parallel 3D FFTs. So I'll show a diagram on the next slide, but I just want to give you logically what has to happen to perform a parallel 3D FFT. And this is basically when you get to the point that you've already smeared charge onto a mesh, that's the starting point. This grid is the starting point for performing the parallel FFT. So initially, that smearing of charge with little forward and reverse communications, that gives you for the grid cells that a processor owns, which would be like a little sub-rig of the 3D domain. That's the portion of the FFT that each processor owns. So there needs to be a communication step to convert that 3D brick decomposition to little thin pencils that extend all the way in the X direction. The diagram will make this clear on the next slide. But then when you have those X dimension pencils, each processor can do a series of 1D FFTs on the pencils that it owns. Now you need to transpose it. The X pencils need to go in the Y direction, so I can do the Y dimension 1D FFTs. Likewise, then the Z dimension 1D FFTs. And when you're to that point, you're now in K-space, the FFT is fully complete, but you do this convolution operation where each grid cell that you own now, in the C direction, is multiplied by a K-space factor. And then you do inverse FFTs to get back to your electric field values. And that can be 3 or 1, depending on the form of P3M you're making. But you need to do a reverse FFT or an inverse FFT. And that's starting here with the 6th step and going back up to the 1st step. So that when you're done, you have FFT results back on this little set of bricks that corresponds to your subdomain. You can use those to put fields on the particles. So typical sizes of FFTs in MD is about 1 grid point per particle. So that means if you're doing a 1,000,000 particle simulation, you need, for example, 100 cube grid to do the FFT. That may seem like a lot, but that's not very big compared to some of the FFTs that people do, like in cosmology simulations or something. I've seen ones there that are like 16,000 cubes, which is a dramatically larger FFT. And the reason I laid out these steps here is you can see the computation steps are actually not that expensive. It's just a small set of 1D FFTs in memory. There's a lot of communication that happens in parallel FFT, and that's often why, as you run on big systems, lots of processors that the FFTs can become a bottleneck. Although Stan was telling me on the Oak Ridge machine, big Oak Ridge machine, figured out some way to do impressively large FFTs reasonably fast. So it's our game. Okay, here's the diagram I promised. So this is an illustration of the steps I just outlined. So this is an 8 by 8 by 8 grid. So just 512 grid points. And I'm imagining here that it's decomposed across 64 processors. What I'm showing is just the domains that are owned in this brick-like decomposition for 4 of those processors. So each processor would own a little 2 by 2 by 2 section of the grid. You have other colors here to try and color everything else. But the initial step is you can't do any 1D FFTs with that decomposition. So you need to change from brick to pencil so that each processor owns, in this case, just a single pencil all the way in the X dimension. Now it has all those 8 values. It can do all a little FFT library to do a 1D FFT values. But then there needs to be this transpose, a pencil to pencil decomposition, so that the red processor now owns all the values in the Y dimension. That allows you to do 1D and FFT, 1D FFT in the Y direction. Likewise, you need to transpose to the Z direction, so you can do all of the entire one-dimensional Z FFT. So that kind of communication for each of these stages, it's a communication to get between each pair of those diagrams. That's the 3 communications in the forward FFT, the same thing in the reverse. You can think of doing that with MPI all-to-all. So saying my 64 processors are going to ship data somewhere else, and that would work. But if you think about it, and these diagrams illustrate it, it's really a few-to-few communication. So look, for example, at these two bottom diagrams. There's 8 processors here, each of which own one of the Y pencils. We want to get to Y pencils in the Z direction. Those 8 processors don't need to talk to the other 64 processors, all this other 64 processors. They only need to exchange information within their little cluster of 8 processors. So those little 8 processors do all-to-all, but another set of 8 processors does all-to-all within that cluster, et cetera, et cetera. So you can think of it as all-to-all, but within small subsets of processors. And in LAMMPS, rather than use the brute force big all-to-all, what's done is to do this with the regular communication, so that we figure it out for the whole set of processors, that 8 processors only end up sending messages to 8 processors, vice versa within each of those layers. So it can be a little more efficient than using the full MPI all-to-all.
I think both are available, right?
Yep, and so that's actually a switch or an option in the code in the input script. You can say in the parallel FFTs, use all-to-all or use a regular. So depending on your problem size, your grid sizes, et cetera, it can be more efficient. Use one of these. Okay, so that's the last description of how irregular communication is used in LAMMPS that I wanted to give. Are there any questions about any of those topics or things I just covered? Okay. All right, so now I'm going to go to how LAMMPS uses the rendezvous communication pattern. So again, recall processors don't know who to send, they don't know who to receive from, but this intermediate rendezvous decomposition is going to solve the problem. So now I'm going to return to those 3 problems I just briefly highlighted and show you in detail how they work. So this was setup of rigid body properties, enumerating bond topology, and this rerun. So before we implemented these rendezvous approaches in LAMMPS, which was a few years ago in collaboration with Chris Knight at Argonne, who I'll thank on the last slide, we were using ring communication for the first 2, that kind of thing where the information passes all the way around. And it works pretty well for small problems and, well, I should say, even for big problems on reasonable numbers of processors. And it was acceptable because it was only a setup operation, but it dramatically failed at large scale, became dominant. So that's what motivated these rendezvous algorithms. And I'm going to show you some findings to show you that this approach can be dramatically faster at scale. So let's talk about the rigid body setup operation first. So here's on the right, sorry, I keep pointing at my screen, this doesn't help you. Here's a single rigid body. And let's say we have a collection, here's a little mixture of 4 of those with different orientations. So this is a case where all the bodies are the same, but as I mentioned earlier, bodies and a collection of rigid bodies and LAMMPS can actually be heterogeneous. They can be different sizes. And if you're an atom, like this red atom here, the only thing you know is you belong to rigid body 7. You don't know who any of the other atoms are, whether you own them or the processors. So what needs to be figured out for the actual rigid body integration to work is we need to figure out a central atom. By central, I mean the atom in the rigid body closest to the geometric center. What the ID of that atom is, because that atom is going to store properties about the rigid body, like its total center of mass, its current orientation, et cetera, et cetera. So that has to be figured out. Then we need to know the distance from that central atom to the furthest atom away in the rigid body. So that would be here represented by that green arrow, the length of that green arrow to that upper right atom. And the reason that's important is we need to ensure that that distance, when we do the partitioning, we define a cutoff, that cutoff is going to encompass that distance so that that central atom can acquire all the information that's needed about it from other atoms in the system. And then finally, all the atoms in that body actually need to know the ID of this central atom so they can look up this information about the current orientation, the center of mass, current position of the center of mass, rotation of the body. Okay, so how do we do that? Here's the rendezvous algorithm idea. What we're going to use as a rendezvous decomposition is we're going to take a set of body IDs. So if we have 1 million molecules, those could be numbers from 1 to 1 million, or they could be more random than that. Maybe the body is numbered by one of the atoms in it, and so the numbers actually go to 2 billion or something like that. But each processor is going to own a hashed subset of body IDs. By hashed means we take an ID and we randomly, we take that ID, which might be a 64-bit integer, and we randomly turn it into a number from 1 to the number of processors. And that's good hashing means that's kind of done completely random. So now, but what that gives us is if we know a body ID, we know who the processor is that owns that ID. That's the rendezvous composition. So each processor is then going to send one datum for each of its atoms, and it's a little tuple that looks like this. It's going to have the body ID in it. That's going to determine which processor to send it to. It's going to have the atom ID for the atom that's in that body. It's going to have the coordinates of that atom, and it's going to have the ID of the processor that actually owns that atom. And so that's going to allow the rendezvous processor for each of the bodies that get assigned to it, sort them into atoms per body, and then do these computations that I just described here pictorially. So the rendezvous processor will receive all of the atoms in some subset of the bodies. If there's M bodies, on average, each processor will own M over P. And it will get all the information for those bodies so it can compute this information. And then it can send back one datum per atom with the atom ID and this ID of the center atom in the body. So that processor, every processor for each of its atoms knows which body it's in. And the max distance, as I mentioned, is used to check the peristaltic cover. Okay, so here, hashing ensures that the communication and the compute works nicely load balanced. So that's why it's nice to use this randomized decomposition for the rendezvous decomposition. So here's some performance numbers. So this was on the biggest MPI base, just no GPUs, no threading really, not much threading was used. The biggest machine at the time, open machine, which was Mira Blue Gene Q machine at ALCF a few years ago. I think it's since been decommissioned, unfortunately. But I'm going to show you in this table timings in a weak scaling sense from 1 node up to 48,000 nodes. And that's 16 cores per node, so that's 750,000 MPI tasks. And I'm going to show you a problem which on 1 node, 16 cores, is 5,000 bodies and about 184,000 atoms. And when you scale that up in a weak sense to the total, to the full machine, or I think maybe 2/3 of the machine, 48,000 nodes, 750 million MPI tasks, I have 258 million, 250 million rigid bodies, and 9 billion atoms. So here's the performance for the original ring algorithm in seconds and the new rendezvous algorithm. So even on 1 node, rendezvous was about 4 times faster, which is on 16 MPI tasks. Then you can see they diverge here. This kind of scales linearly. This scales as N over P. By the time you get out here, you have these ratios out here. So the ring algorithm is that each processor is scanning all the data to find the ones in the bodies that it needs. Rendezvous is each processor who is receiving exactly the set of information it needs to do rigid body computation on a subset of the bodies. These asterisk timings are actually estimates. As you can see, they're nice projections of this linear scaling. We're going up 4x in size here and 3x in size here. We didn't want to run for 6,000 seconds, 2 hours, in order to set up the rigid body simulation. But it's 4x faster here. It's about 700x faster here. We used to use the rendezvous algorithm, which is the ring. So if you're running on 256 nodes, this 47 million atom simulation, you might not care. If you're going to run a couple hours and it took 30 seconds to set up, that would be exceptional. That's where we were before. But if you're running this really big simulation and you have a few hours on the machine, you do care that it takes 2 hours to set up the simulation. So that's why we like to treat the faster number. Okay, now I'm going to talk briefly about the bond topology enumeration. So this is treating the molecule as a graph and trying to identify which are your first neighbors, your second neighbors, your third neighbors in that graph. And that's needed in LAMMPS for weighting factors on the pairwise computations, because for many molecular force fields, you don't apply the full Coulombic or the full Leonard-Jones interaction, depending on those weighting factors as you go out in the topology. So what I mean by enumerating things, let's say you're interested in this red atom, here's the topology of the molecule. This is showing all the third neighbors, 3 hops away on the bond topology, all the third neighbors of that red atom, these green. So that's what needs to be enumerated by LAMMPS, stored with the atoms, so that when you compute neighbor lists, compute pairwise actions, and apply these weighting factors. So the rendezvous algorithm is quite nice for doing this conceptually. You do it once for each level of neighbors. You run one pass of rendezvous to get first neighbors, another pass to get second neighbors, third neighbors, etc. So I'm going to illustrate here in text or words how to get second neighbors once you already know the first neighbors. So the rendezvous decomposition is to have each processor own a repeat atom. So if you have atoms numbered from 1 to 1,000,000,000, running on 1,000 processors, then the first processor owns atom 1, atom 1,001, 2,001, etc. Every processor does something similar. So the first stage is we're going to send one data that has the atom ID and the processor who owns it. We're going to send that to the processor who owns that atom rendezvous decomposition. And then the processors that own the atoms in LAMMPS, they're going to do it. They know the first neighbors of each atom. They're going to do a little double loop over their first neighbors. So if this atom has 6 neighbors that it's bonded to, it's going to do a single loop over 6, and then it's going to do another loop. So it's going to basically enumerate every pair of coupled first neighbors. And the reason is, if you think about, if this is the atom and it has 2 neighbors here, these 2 atoms are second neighbors of each other. So this processor knows these are second neighbors, but it's those atoms that need to store that information. And we don't know what processors own those atoms. That's what the rendezvous decomposition is going to accomplish. So in that double loop, if J does not equal K, then we're going to send the JK pair to the processor that owns J, and we're going to send the JK pair to the processor that owns K in the rendezvous decomposition. And actually, we only need to do this if one of these atoms is a ghost, because otherwise, if we own all the atoms, we could actually set the fact that they're second neighbors right now. So we're doing this just kind of on the shell of atoms that are around the edge of my domain, where they're coupled to ghost atoms. And I should say that at this point, this computation is done very early in the setup before we've even defined or acquired ghost atoms. So all we really know is our own atoms. We don't know anything else about the topology of the molecules or where they go or who. All we know is that we own some atoms and we don't know anything about atoms we don't know. Okay, so what the rendezvous processor does, it doesn't really have to do any computation. It just sends that JK atom back to the owner of the J atom and to the owner of the K atom, because it owned it in the rendezvous decomposition, but it also knows, because of this first step here, it knows for each of the atoms it might get a message for. It knows who the actual processor is. So it's basically the mailbox that's letting you forward something from processor I to J, because the rendezvous decomposition knows that. Okay, so if you were going to do third neighbors, it would now be a double loop over your first neighbors and your second neighbors, and every pair of atoms in that double loop, those would be third neighbors of each other. So you can see how you bootstrap yourself up to fourth neighbors or fifth neighbors successfully. Okay, so here's the timings again on the Blue Gene Q machine at the LCF. Now we're starting with 64 nodes going up to the 48,000 again, 750,000 MPI task. 48 million atoms here on 64 nodes, 37 billion atoms for a huge molecular system on that many nodes. And now, again, we had a ring version of this algorithm originally. The asterisk timings or estimates would have taken like a day to do the ring algorithm on 48,000 processors for 37 billion atoms. But now it's already about 100 times faster on 64 nodes. I think I have the ratio there, 5,000 times faster on the full machine for the very big problem. Okay. Any questions about that?
Quick question. I imagine the performance here depends a bit on the topology, right? Like, depending on, how many bonded neighbors, on average, they have. I'm curious, was this like a linear polymer, or do you know what kind of?
Oh no, this was an all atom simulation, so it was like a coarse grain string model. So typically the bond, what's the maximum bonding factor is 4-ish, something like that. Yeah, but it could be it doesn't the maximum number of bonds is important. You're right in how much sort of looping you have to do to generate these things, but but it doesn't matter how complex the topology is if it's still walking.
Right.
Okay, the last sort of concrete example here is this rerun command in LAMMPS that lets you perform a second run using only dump snapshots from a previous run. And motivating use cases are if you didn't calculate some diagnostic in the first simulation, but you want to take each of these snapshots and compute the diagnostic on that simulation. So it might be per atom stresses or per atom forces or energies or whatever that might be. You could also even change the peristyle and say, I ran this simulation with one peristyle, but if I had these dynamics, here's the results, the diagnostics I would have gotten if I was using the second peristyle on these snapshots from the first peristyle. So the challenge is when you do a very large simulation in NRP, parallel I/O is often used for these snapshots. And so each snapshot itself may be spread across multiple files. You might have a whole bunch of those snapshots. And really, to minimize the I/O cost, you want to read those snapshots as quickly as possible, also in parallel. You might be running on a different number of processors now to do the second run that you did on the first. So similar to the restart, now you're reading things in, but what you've read in has nothing to do with the atoms you owned on the previous snapshot. But you need to maintain information about atoms except the coordinates on the new snapshot, because things like the atom type, things like maybe the atom mass, if it has a per atom mass, other information is pertinent to those atoms that you need to retain, or its place in the bond topology. So another case can be that the new snapshot, because you were running NPT or something like that, has a different box size and shape. And so that may also be different than the old snapshot. And if the snapshots were 1 million steps apart, it could be dramatically different. So the question is how to map these new coordinates to the old atoms and also get the new old atoms to a new spatial decomposition. So here's how the rerun command can do that. It's with a rendezvous plus irregular solution. We're really going to consider 3 decompositions of atoms. So I'm calling AD the arbitrary decomposition. That is the way you read in the atoms from the dump file. That could just depend on how fast you did it or which files those atoms were in. So a processor could own basically any atoms. The SD is the spatial decomposition of the old atoms from the previous snapshot. And RD is going to be the rendezvous decomposition where we again assign every PEEP atom to a processor. So what the rendezvous decomposition enables is the SD processors can now send the atom ID and the proc ID to the rendezvous decomposition to say, I'm the guy who owns this atom. The AD processors can send the atom ID and its new coordinates also to the rendezvous decomposition. And then the rendezvous decomposition can take those 2 sets of information and send for an atom ID its new coordinates back to the spatial decomposition. That's the old decomposition, so now we can do the irregular communication, migrate those atoms long distances to the new decomposition. So I don't have specific timings for this, but here was a use case that motivated us to implement a rendezvous algorithm for rerun. And this is work by a group at Lawrence Livermore doing really huge simulations in this Nature paper. These were metal deformations of dislocation formations and dynamics as they applied dramatic strains and stresses to a chunk of metal. It's about a 2 billion atom simulation. They saved thousands of snapshots, ran on 500,000 cores, another Blue Gene Q machine at Livermore. And after the fact, they wanted to do post-analysis and use the rerun command, not on this big a chunk of the machine, but on tens of thousands of cores, compute new things about how these dislocations were interacting in that snapshot. So when they started to use the rerun command, it wasn't using this rendezvous algorithm. It was dreadfully slow to process this volume of data after the fact. So we implemented this rendezvous approach. I don't have specific times, but according to Alex Stokowski, it now has very little overhead to reset these atom cores. All the time is spent doing the analysis, so they can now be fairly productive, which they weren't able to do without use of it. Okay, how we doing? 20, yeah. I think I got about, probably got about 10 or 15 minutes left, so I think we're good. Okay, any questions about rendezvous communication? Okay, so now I want to give you one example from this other code, Sparta DSMC code. It's a direct simulation Monte Carlo method. That's what DSMC stands for. It's another open source code, and myself and Stan and some other collaborators at Sandeep were the main developers of this, still are in Stan's case. I still do some work on this code as well, but you can go to that website if you want to learn more about it. DSMC is kind of a generic name, which doesn't mean anything, but it's a simulation technique for modeling rarefied gas flows. Rarefied means low density. And so the common use case is you have a spacecraft that's re-entering the upper atmosphere, and the density may be changing as you come down through the atmosphere, but you want to model the flows of the gas around that spacecraft. So you can typically use either in that scenario or doing some study of turbulence without the spacecraft, which is turbulence for different kinds of flows. You can use tens of billions of gas particles. Hierarchical grids are used, which I'll illustrate in a moment, with up to billions of grid cells. And the purpose of the grid cells is each time step you want to co-locate particles that are close to each other and be able to do Monte Carlo collisions in chemistry between pairs of those particles chosen randomly. So if you have a surface, it might be represented by as many as millions of triangles for a complex spacecraft, or even more triangles than that for at a very tiny scale for a fibrous heat shield, which I'll show you. So here's three little pictures from Sparta simulations. This is flow around the NASA shuttle, the Mir space station. And then this is a little snapshot. The length scale here is about 1 millimeter on a side. This little fibrous heat shield material that has detail at a very fine scale. And this has fairly low density actually, but it's used, that's why it's nice as a heat shield, because it will absorb the heat and protect, doesn't conduct the heat very quickly the surface of the space shuttle wing, for example. Okay, so the computational task here is in order to do these simulations, we have to map surface triangles to grid cells in Sparta. So here's a picture of one of these adaptive grid. This is flow around the Apollo space capsule coming back into the atmosphere. And it's a 2D slice through a 3D model, but you can see 5 levels of different grid cells here. These are not particles, these are the actual grid cells getting smaller and smaller in the wake of the flow around the spacecraft. And so each grid cell needs a list of triangles that intersect that grid cell on the surface, either of the space capsule in this case, or here's a little idealized model of that fibrous material made of lots of tiny little pencils, each made up of hundreds or thousands of triangles. And you need to know for each grid cell which triangles are in it, so that when you eject a particle through that grid cell, you can check for collisions with each of those triangles. So for small triangle counts, it's very fast to just let each grid cell check against all the triangles. So if you have 100 or 1,000 grid cells or triangles, I mean, you can easily kind of do this algorithm in that simple way. But if you have a lot of triangles, it's faster to actually flip this and let each processor just loop over a subset of the triangles that it owns for this purpose. And for each triangle, identify, use a bounding box around the triangle and identify what portion of the grid you need to do the careful checks on for intersections. And so what you end up with at the end of that is for each triangle, you end up with a list of grid cells that it intersects. So the problem is those results are exactly the opposite of how the code needs. So what do I mean by that? As I said, you know the list of grid cell IDs that intersect each triangle. What you really need to know is the list of triangle IDs that intersect each grid cell. That's what the advection part of the time stepping needs. You know you're in this grid cell, look at the 5 triangles that intersect it, and I can detect those collisions. So how would you sort of invert this data set? There's a question for you. This time I'm really going to ask the question. How would you invert this data set, knowing grid cells for each triangle? Triangles have IDs as well. What you want is for each triangle or for each grid cell, you want to know the triangles that intersect. So how would you invert this data set with a rendezvous algorithm? Ideas? Okay, so again, you have grid cell IDs and triangle IDs. So the rendezvous decomposition is that each processor own a hashed randomized subset of the grid cell IDs. And then the rendezvous part is very simple. For each, you have a set of triangle with a bunch of grids that intersect it. You pair that up and send send 2 things. First is you also own in the Sparta decomposition. Each processor owns some grid cells. So you tell the rendezvous decomposition, I'm the owner of this grid cell. send the grid ID and your processor ID. Sorry, point to the screen. But then from the triangle, for each triangle, you have a list of grid cell IDs that intersect it. Chop that up into little datums. You send the grid ID and the triangle ID for that intersection. So now the rendezvous processor takes all the datums it gets and it sends back to the grid at the owner of the processor that owns the grid cell ID. It sends that triangle ID. So that processor receives the list of 5 triangles that intersected back to that processor, and it can store it right where it needs to store. Do you understand how the data is kind of in the wrong place and the rendezvous allows it to be reorganized in the right place? Because you're sending it to this intermediate processor who gets information from one place but can send it back to the right place.
Can you go back one slide?
Yep.
So you know the grid cell IDs, and that's why you have to use those as the rendezvous decomposition.
Yeah, and it's because the owners of the grid cell IDs are the ones who need to store the list of triangles for each grid cell intersection. They're the ultimate customer of that information. Okay, so here's a few timings again. This is not weak scaling now, it's sort of strong scaling in the context of the number of triangles anyway. So I think this was Blue Gene Q again from 64 nodes up to 10, 16,000, 16 cores per processor. So that's 250,000 MPI tasks. The surface counts here are mostly 1.3 million, but we did one largely with 2 million. And so the grid cells vary from 1 million up to 256 million. But here's the old algorithm, which wasn't a ring communication. It was something that was kind of more heuristic specific to this problem. But it worked pretty well. These times started to get too big. And so we implemented the rendezvous, which is just sort of an abstraction of black box algorithm that's not really tailored to this problem specifically. And now, 3 seconds versus 105, a speed up of 30, here a speed up of the ratio there, 170x faster. So this rendezvous algorithm did tackle things much quicker. And again, this is a setup operation. So it's okay, to spend a couple hundred seconds if you're going to simulate for 6 hours or something, but if it takes a half hour to do the setup, that's kind of. And I should say these rendezvous timings, the actual communication itself is a small fraction. All this checking for the intersections and other things is also done in there. So most of that is computation, which is now nicely load balanced. Communication is just a small fraction. Okay, so one last example for rendezvous where I'm going to see if you can come up with the rendezvous of it. So this is an example of doing post-processing trajectory analysis for an MD simulation. So imagine that you have a cell membrane modeled here. This is just showing an idealized one, but it could be an all-atom one. And imagine there's some ion channels and some water channels in it. And imagine you have things, ions or water molecules that are going to pass through those channels. You're doing a very long time scale simulation, writing out snapshots. So in the case of the solvated lipid cell membrane, you want statistics on atoms that enter the channel, back out, atoms that go through the channel, maybe it comes back through it the other way. Another time, you want to generate statistics from your big simulation about all of those special events. Conversely, you might have a large solvated protein that has many docking sites on it, or maybe it's a collection of proteins, and it's solvated or has other ions or small molecules around it, and you want statistics on close approaches to that docking site by other molecules or other atoms. And you want to know, did it get close? How close did it get? Did it dock? Did it undock? What it did. So basically, again, this is sort of post-processing the big data set to see where atoms travel. So imagine you have a 1,000,000 atom simulation, you have millions of snapshots, you ran it on thousands of processors. How are you going to do this? So note that when you read in the data after the fact, this is a post-processing step. If you read it in after the fact and each processor stores a few snapshots, that data is stored exactly wrong to do the kind of analysis you want to do. You think of the data as a 2D matrix. You number your atoms along the rows, you number your time steps up here. You're reading it in as a snapshot, you're reading in columns. What you really want on a processor is a row. So that for one atom, I know all the positions that went across the entire simulation. And now I can do all this kind of statistics stuff. See where that atom went, what it got close to, et cetera, et cetera. So, question is here, how would you do that with a rendezvous? Basically, it's we want to transpose this matrix. So imagine I read a snapshot. I have for all the atoms in this snapshot, I have atom IDs and coordinates for each atom, and I also have timestamp for the snapshot. We have to decide on a rendezvous decomposition, and we have to decide what we're going to say. And so in this case, the rendezvous decomposition is where we're going to do the trajectory.
So
We
could
don't bias
you,
and
could you do it like over atom IDs?
Yeah.
And then,
Let's use atom IDs. So we randomly assign atom IDs to processors. If there's 1 million atoms and 100 processors, we just give 10,000 IDs to each processor. So now, what do I need to send from the snapshot that I read? What do I need to send out?
each atom position and the time.
So for each atom, I look at the ID, I can map that to the rendezvous processor. And I can say, I'm going to send this atom to that processor. I give it the ID, I give it the coordinates from that snapshot, and I give it the timestamp. So now, on the other end of it, the processor receives for atom 37, it receives messages from a whole bunch of different processors that have 1 million time steps for that atom. So I collect all the ones that are for atom 37. I sort the timestamps. I have the coordinates for each timestamp. Now I have the entire trajectory. So, and I may have 5,000 atoms that were assigned, but I have that for each of the 5,000 atoms. I can do analysis on 5,000 of those atoms, and the other processors do it on different subsets. Okay, so that's a case where rendezvous doesn't need to send anything back. It's just an alternate decomposition, transpose the data set, get the atoms where I, or to get information, all the information about one atom where I can do the analysis. That makes sense? Okay.
So is the rendezvous, like a ring is never better than a rendezvous?
Yeah, it wouldn't be. In this case, you have to circulate all your atoms around the ring, P steps, and I know I need stuff about atom 37. So every time some new chunk of atoms came to me, looking for atom 37. So that would be inefficient.
As far as I understand, the ring is when you need everything with everything. And then you have the complexity anyway.
Yeah.
So you're just running in parallel, but the computational complexity of everything with everything will just explode in your face when you have a large system.
Yeah. Literally was an n squared computation.
Yeah.
That'd be the only way to do it without. Well,
Okay.
okay, in this case, we only need information for a subset of the atom. We only need one peak of the information. We just don't know who has it. They don't know
Yeah.
that I'm the one who needs it with the rendezvous decomposition. Okay? Okay, so at the very end, I'm going to come back to this example for just a moment to make one more connection. But now, there's no more questions about rendezvous communication. I just want to show you a couple slides, 3 slides, I think, of pseudocode for how to implement LAMMPS. So here's how forward communication works in LAMMPS in a pseudocode sense. N swaps is the number of sends and receives, exchanges I need to do with other processors. Each one might be not sending and receiving from the same processor, because I could be sending to the left, receiving from the right. But the number of swaps is the same, they're all swaps. So I loop over the swaps, I make a call back to the caller and say, this is the number of sends I need to do, the number of things I need to send in this swap, and I send the list of atoms that I need back in that message. It puts them into SBOF. And now if the processor is me, maybe because I'm passing across a periodic boundary to myself as ghost atom, And I don't need to actually do the MPI calls, so I just set R buffer, receive buffer, send buffer. But otherwise, I post a receive for a message into my R buffer. And I know the processor that's going to send to me. I know the amount of information that it's going to send to me. And I post a request. I do my send of my SBUF, and I wait on that request to say that I've got this information. And then whether I'm doing it on my own data or the data I received, I do an unpack caller to put that atom information, that buffer of information with the correct atoms that I received. So caller can be an atom, a pair, a fix, a compute, a bond, a dump style, as I said. In all cases, that pack and unpack is provided by the caller, so it knows exactly what information to put in. And that allows the caller to control what per atom data is sent forward sent. And reverse comm is very similar to this, just with the altered pattern I showed you. Okay, here's pseudocode for the irregular communication. And I'm going to show this in two parts. What the caller, the class that wants to do the irregular communication does. And then in the comm class, the little kernel that does the actual irregular communication. So the caller knows it needs to send out, let's say this is in the case of load balance, knows I need to send 2/3 of my atoms someplace else. So it knows the number of things I need to send. So it allocates a buffer to hold that information, and then it loops over its atoms and it sets for each one, for each of these end send datums, it sets the processor I know I need to send it to. And I fill up the SBUF with that end send number of quantities. And now I do the irregular communication in two steps, one to create the plan and one to actually exchange the data. So a plan is going to store information about how it's going to do that MPI reduce scatter. It's going to store the information about how many messages I'm sending, how big they are, et cetera, et cetera. So what comes back from this call is the number of datums I'm going to receive, which I didn't know in advance. This is the total number, so I can allocate space for them. And then I exchange the data by sending in what I want to send, getting back what I want to receive. So end send and end receive, the number of datums and sending and receiving are typically not the same in this case. Create plan invokes that reduce scatter operation, stores all the info that's needed to do this exchange data. So now the next slide, I'm going to show you in the irregular class how this exchange data. So it receives these two buffers of information, or receives one buffer and sends back. So this is done with a loop over all the receives I need to do from other processors that was figured out by the create plan part. And then post the receives for all the data I'm going to receive, offsetting into RBUF by the appropriate size. And used to be we invoked a barrier here to make sure all the receives were posted before we did any sends. But in the modern MPI, that doesn't seem to be necessary. I think sends can either get queued or they get triggered when the receive is posted. So you don't need to actually force the barrier. But then I loop over all my sends. But it is important to have all these receives posted before somebody else starts sending me information, because I don't want to make copies of it. I want it to go where it needs to go. So after that, if there's anything I'm essentially sending to myself, like across the periodic boundary when I'm on the other side, I didn't need to do the sends and the receives for that. I just copy the data from the SBUF into the RBUF. But then I wait for all the requests that I posted to be satisfied, because that means I filled my RBUF and I can return the call. So that's why this is different than regular communication, where I would be doing post one receive, do one send, post one receive, do send. Here, I need to post all the receives, then one send. Okay, last bit of pseudocode. This is a black box implementation of the rendezvous communication. So here's the method that's in one of the comm classes. I'm passing in some number of input datums for these little tuples of information. This is just a vector of all those n datums. I'm also flagging each one with the processor in the rendezvous decomposition that I want to send it to. And then I give it a prototype for a callback function that's in the call. So the first communication can be this kind of all-to-all communication where I'm taking this set of in data, telling it which processor each one goes to, and it gets received at the other end of MPI all-to-all in the rendezvous decomposition with a subset of data from everybody else that I received, and also the number of data that I received. Those two things are the arguments to the callback, so that now the processor in the callback is doing computation of rendezvous decomposition. That's going to produce potentially a new set of output data and a new set of processors to send. It's figured out in the callback. Now we do the second round of communication, which is taking this number of datums and out data, sending it back to another decomposition. So the output of that is the out data and the number of outs, and that's what's returned here to the call. So depending on what kind of rendezvous, you might not do both communications, you might just do everything in the rendezvous decomposition done, but the method gives you the flexibility to determine. So I've shown it with two all-to-all communications, sandwiching this callback to the caller, which is the computation that's performed on the rendezvous data and the rendezvous decomposition. And a computation, the ones I illustrated, it's as simple as just reorganizing the data, sending it somewhere else. It's not actually doing the computation. But you can also use irregular communication operations instead of these MPI all-to-alls. And that's typically faster if each processor is effectively only sending data to a few processors and vice versa. All-to-all can be faster if each processor is sending to essentially all the processors data back from all the processors. So typically, like in the grid transfer case, irregular is better if you're sort of using a geometric decomposition for the rendezvous decomposition. If it's one of these randomized or repeat that, and that's kind of a random decomposition also. Typically faster. Okay, any questions about the code details?
I'm Fred.
Oh, I see.
Yeah. Sorry I'm late.
Oh, that's okay.
I missed my train.
You're just in time for lunch.
I know.
Okay. Any questions about code details?
I saw that sometimes you use MPR send and sometimes MPI send. Is there a specific reason?
Trying to remember what RSend does.
Documentation says it's a ready send, but it
Oh,
doesn't
that's
tell.
right. Okay, so ready means you're positive that the message that the receive has been posted. And there are a couple cases, kind of variants of what I talked about, where we do know that's the case. We do a barrier in there, and that's typically more in the setup than in the regular communication of the data itself. But you can, a ready send will be a little faster if the barrier is there and you know that the receive has been posted. Okay, so just a couple more slides. So I want to come back to this communication pattern in the rendezvous example I took. So this was the one where we had the cell membrane. We were looking for crossings of the membrane, close approaches to the docking sites. So this was to analyze MD trajectories using the rendezvous composition to effectively transpose this 2D matrix where things were stored by snapshot versus things are stored by atoms. So this example is actually not one I came up with. It came from this paper, which is from the D.E. Shah group, and Tiankai Tu was the lead author, called Scalable Parallel Framework for Analyzing Terascale. This is back when Terascale was a big deal in 2000. Terascale MD trajectories, and it was at Supercomputer in 2000. And I was a reviewer of this paper, so I learned what they did. And in their case, they had 1 million atoms. They had 100 million snapshots. It was a really long biological simulation. So they had 3 petabytes of data. This was back when a petabyte was big enough. Maybe it's still a fairly big amount of data.
It is.
Even though there's only terascale in the files. But here's the interesting thing. They did not use a rendezvous for solving this problem. What they used is something called MapReduce. And it was written on what was not one, well, that was novel, using it in this context, but also they wrote an MPI version. It was also accepted in the paper. I think it got presented at the conference. So does anybody know what MapReduce is? This was something that was really a hot topic about 10 or 15 years. Has anybody even heard of MapReduce?
I can think of a MapReduce, but I don't know if it's the same thing that
Okay.
you're thinking of.
Well, okay, I'll show you on the next slide and you tell me if it's the same thing.
Yeah.
So MapReduce, you can think of it in the context of my talk here, it's like a rendezvous communication on steroids. So MapReduce, the term was coined by Google. Well, it was actually coined, I think, in the Lisp language decades ago. But I'm not sure quite why it made this connection for Google. People from Google wrote a paper. They didn't release any code because they wanted to keep it in-house as proprietary software, but they released the idea of how they use this as to allow easy parallel out-of-core processing huge data sets that Google stores. So they would run MapReduce in parallel on their computers. It was like a scripting. But there were some open source people that founded a company called Hadoop, who made an open source version. So Hadoop is like an open source version of MapReduce that they distributed widely and got collaborators on, more powerful. And other companies who weren't Google, and especially the tech companies, could use it to process their. So this is the context. I was talking about MapReduce. Is that the context you're thinking?
MapReduce is just a function in programming language that I always use that, if you have, if you want to reduce the dimensionality of your data, it applies an arbitrary function to the data at the same time before it
Is
was.
this Python?
No, it's in Julia. It might be in Python too. I don't know.
So
it might be
maybe that
something
connects back to the Lisp usage decades ago.
Right,
Lisp
I think
was
so.
Kind of precursor of some of these.
Right, because it doesn't necessarily need to be parallel. It's just, just
Okay.
arbitrary function.
All right, so here's the MapReduce solution to that trajectory problem with the data being in the wrong place. You perform an initial operation, which is to read a snapshot. And this can be done, hundreds or thousands of processors can each be reading a snapshot. And you emit what are called key value pairs. So the key in this case is the ID of the atom, and the value is the timestamp and the XYZ coordinates. So this should now be sounding kind of like the rendezvous level. Then there's a communicate step, which based on these keys aggregates all keys with the same ID to some arbitrary processor. And so all the values get appended together based on this key and gets handed to a processor. So now, different set of processors or arbitrary set of processors in MapReduce, in these things, you don't have any idea what processor is performing the computations. That's all. You're just passing it a bunch of files. You define what the keys and the ID, the keys and the values are, and it parses the files, and then data gets shipped wherever. Reduced part is to take whatever processor got that ID with its set of values. It can then order the values based on the timestamps, and then it can do the analysis, trajectory analysis. So the fundamental MapReduce communication operation, this communicate operation, Hadoop calls it a shuffling the data. It's like transposing the data in our example. It's done out of core using remote file writes. So in this big cluster, processors are writing chunks of data to other processors into their file systems, doing any kind of MPI communication. But that shuffle is conceptually identical to an MPI call. You've identified other processors. Here you have to actually, an MPI, you have to identify the processor, as opposed to just put them in the cloud, let them landscape. But with that, you're saying data gets shipped out to other places, and I'm doing, because of the way I organize the MPI all, I'm making sure everything with the same key, the atom ID in this case, aggregates the same. So think of rendezvous.com as I described it as a subset. It was more general. We don't do MPI on out-of-core stuff. Try not to run anything out of core on a big parallel machine. We have to know, we have to decide on the decompositions, that kind of stuff. This is much more arbitrary, but it works for processing these huge data sets in ways that are not really scientific computing usually, but are designed for letting something be parallel in a dramatic way when the data is scattered all over, make sure it aggregates the way you do the computation that you want. So this paper, this was again about probably 15 years ago now, got me interested in implementing MapReduces with MPI. So myself and a collaborator, I'll thank on the next slide, wrote a little MapReduce library that doesn't really have any dependencies. It's just a pretty tiny piece of software. I think it might be useful in a scientific computing context. You're welcome to download it. The GitHub site is there. But we used it for graph algorithms, where the graphs can be kind of very topologically irregular. These are not molecules, these are just arbitrary relationship graphs. And we could do things like connected component algorithms, which is finding a sort of motif within that distributed graph. We could do that with a MapReduce version. So it was kind of cool. Okay, so Before I summarize, anything further questions on what I talked about? Okay, so just in summary, I've told you about 4 communication patterns used in LAMMPS: regular, irregular, rendezvous, and ring with a little bonus connection to MapReduce. I think they're useful in many scientific simulations, and they're useful to understand, even if you don't write MPI code yourself. It might be nice to understand basically what's going on behind the scenes, so you think of it in the context of what your model, say, that you might implement in LAMMPS needs. The rendezvous one is probably the one that's least familiar to people, so I'll just summarize its attributes. It's useful when you don't know who to send data to, you don't know who you're going to receive data from. But it allows you to move data where it's needed via the rendezvous decomposition. You can auto load balance if you randomly spread that data out, and it's most advantageous at really large scale, large and large. And the reason it works pretty well on big parallel machines is it's leveraging the huge bisection bandwidth communication those machines support. That's what they have, that it's cheap plus it's a really fast communication. So here's a question. Does my talk have anything to do with GPUs? I think the answer is no, not really. That was Stan's talk yesterday. So the MPI, I talked all about MPI calls, now this communication stuff. Those are the same, whether those MPI calls are working on CPU memory or GPU memory, as Stan talked about. You can make the same MPI calls just using pointers into GPU memory. And so one thing LAMMPS tries to do, I didn't really talk about the pack unpack part, but that was kind of a kernel in all of these communications. So LAMMPS tries to parallelize on the GPU, packing and unpacking these messages. So if I know I'm going to send data to 22 processors, if I can pack them all in one kernel, 22 buffers for regions of the JSON buffers, then when I get ready to do the MPI, I can get off the kernel, get off the GPU, do it quickly using the pointers to the GPU buffers. One last high-level lesson to keep in mind, and that is a lesson I've learned from working on various simulation codes, is that if possible, it's usually better to try to load balance individual computations, either within the same simulation or maybe computations within a multi-physics or multi-scale computation, to balance each stages. And that may mean that different computations need different decompositions of the data in order to perform optimally. And that means you have to do some extra cost for communication in between. But I think that's often better to pay that extra cost than it is to run all the stages, same decomposition, and have poorly load balance, because then that's more expensive communication that you hopefully can do with these patterns to make it relatively cheap to rebalance or to generate a different decomposition. So with that, my last slide, as I said, I want to thank Chris Knight at Argonne, who's been a collaborator for several years on these rendezvous algorithms. Karen Define is the person in Sandia who worked with me on this MapReduce for MPI idea I mentioned. And here's 3 papers which have more details about stuff I talked about today. One is the LAMMPS overview paper in 2022 that talks about basic communication algorithms in more detail than I talked about here. If you're interested in specifically the rendezvous algorithms, go to a paper with Chris Knight, 2021, Journal of Parallel and Distributed Computing, that talks about lots of detail or lots of examples for LAMMPS and Spark. Was useful. And the original rendezvous paper that I did with collaborator Bruce Hendrickson and Jim Stewart when they were at Sandia was back in 2004, this grid transfer idea. You can see some of the original motivation for that older paper. So here's the Sparta website again, and if you want to look at actual LAMMPS source code files that have the pseudocode I talked about, there's the various COM files for both brick and file decompositions. There's the irregular class. K-space, that's where the FFT 3D and remap of operations that use the regular communication. So with that, I will be done. And did I, yeah, hit 5 something? All right. Thanks for your comments and the little discussions we had. I was hoping to keep you awake for asking a few questions. Done. Want me to stop sharing this?